Hello there, and welcome. Tonight I want to take you somewhere special, somewhere beyond the gentle glow of your bedside lamp, beyond the soft sounds of the night outside your window. I want to take you into the vast, quiet embrace of space, where a secret has been hiding in plain sight for billions of years. It's a secret about falling, about floating, about the delicate dance that keeps our world spinning safely through the darkness. And perhaps, just perhaps, as we explore this mystery together, you'll find that the answer has been with you all along, written in the very motion of your breath, in the way your body knows how to rest even while the earth beneath you spins at 1,000 miles per hour. Before we begin this journey together, I'd love to know where you're listening from tonight. What corner of our spinning world holds you as you settle in? Is it late where you are, with stars beginning to peek through the darkness? Or perhaps you're stealing a moment of rest in the afternoon, letting the day's concerns drift away like clouds across a summer sky. Whatever time it is, wherever you are, you're part of something magnificent that we're about to explore together. And if this gentle voyage through the cosmos feels right to you, if you find comfort in these quiet explorations of the universe's mysteries, perhaps you might consider subscribing so we can meet here again, in this peaceful space between waking and sleeping, between knowing and wondering. The question I want to share with you tonight might sound unsettling at first, but I promise you, it opens into wonder rather than worry. What if I told you that every planet in our solar system, including the Earth beneath you right now, is slowly, continuously falling toward the sun? And what if I told you that this falling is not a catastrophe waiting to happen, but rather the very thing that keeps us safe, that maintains the delicate balance of our cosmic neighborhood? It's a paradox that has puzzled and delighted scientists for centuries, and tonight we're going to unravel it together, thread by gentle thread. You see, when we think of falling, we usually imagine something dropping straight down, accelerating toward an inevitable collision. We think of a stone dropped into a well or a leaf drifting down from a tree, but what if falling could be something else entirely? What if falling could be circular, continuous, eternal? What if falling could feel exactly like floating, like the sensation you might experience right now as you sink deeper into your bed, supported and held even as gravity pulls gently at every atom of your being? This is the secret of orbital motion, the quiet truth that governs every planet, every moon, every speck of dust that circles a star. We're all falling, always falling, but we're falling in such a perfect way that we never actually fall. We're missing the sun by exactly the right amount, moment after moment, century after century, eon after eon. And the reason we don't notice this perpetual fall is beautifully simple. When everything around you is falling at the same rate, in the same direction, falling feels exactly like stillness. Imagine, if you will, being in an elevator that's descending so smoothly, so perfectly, that you can't feel the motion at all. The cup of water in your hand doesn't slosh. The flame of a candle burns straight up. Everything seems perfectly still, perfectly normal. This is what we call free fall, and it's the state that every orbiting body exists in, including our Earth. We're in a cosmic elevator that's been falling for 4.5 billion years, and it will keep falling for billions more, never reaching the bottom because there is no bottom, only the continuous curve of space-time that guides our path. The first person to truly understand this was Isaac Newton, and the story of his revelation is as gentle as it is profound. Picture him sitting in an orchard, perhaps on an evening not unlike this one, watching the moon rise above the trees. An apple falls nearby, following that familiar straight path toward the ground. But Newton's genius was in seeing the connection between that falling apple and the rising moon. What if, he wondered, the moon was also falling, just like the apple? What if it was simply moving sideways fast enough that it kept missing the Earth? Newton imagined firing a cannonball from the top of a very tall mountain. Fire it with a normal amount of force, and it would arc through the air and crash back to Earth some distance away. Fire it harder, and it would travel farther before landing. But what if you could fire it so fast that as it fell toward the Earth's surface curved away beneath it at exactly the same rate? The cannonball would fall and fall and fall, but it would never hit the ground. It would be in orbit, falling forever around the Earth. This is exactly what's happening with our planet and the sun. We're that cannonball, fired long ago when the solar system was young, given just the right sideways velocity by the swirling disk of gas and dust from which we formed. We've been falling toward the sun ever since, but we're moving sideways so fast that we keep missing it. It's a miss that has lasted billions of years and will last billions more, a cosmic dance of near misses that creates the stable, life-giving orbit we call home. But here's where the mystery deepens, where the question becomes even more intriguing. You see, orbits aren't perfectly stable. They're influenced by countless subtle forces, tiny pushes and pulls that accumulate over vast stretches of time. The solar wind streaming out from the sun exerts a gentle pressure on everything it touches. The gravitational pull of Jupiter creates tiny perturbations in Earth's orbit. Even the light from the sun itself carries momentum, giving planets an almost imperceptible push. And yes, there are forces that do cause planets to spiral very, very slowly inward or outward over cosmic timescales. Scientists have measured these effects with extraordinary precision. They've tracked the orbits of planets with radar and lasers, timing their passages down to fractions of a second. They've sent spacecraft to orbit other worlds, using their trajectories to map the gravitational field of the solar system with unprecedented accuracy. And what they've found is both reassuring and fascinating. Yes, orbits do change, but the changes are so slow, so gentle, that they're almost like watching a mountain erode one grain of sand at a time. Take Mercury, for instance. The innermost planet, the one you might expect to be most affected by the sun's pull. Its orbit does indeed precess, meaning the point of its closest approach to the sun slowly rotates around the star. But this precession amounts to just 43 arc-seconds per century beyond what Newton's laws predict. That's such a tiny amount that it took the genius of Einstein and his theory of general relativity to explain it. The sun's gravity actually warps the fabric of space-time around it, creating a subtle twist in Mercury's path that accumulates over millions of orbits. This brings us to an even deeper understanding of what it means to fall. In Einstein's universe, massive objects like the sun don't pull on planets in the traditional sense. Instead, they curve space-time itself, creating valleys and slopes in the fabric of reality. Planets follow the straightest possible path through this curved landscape, like marbles rolling along the inside of a bowl. They're not being pulled so much as guided, following the geometry of space itself. Imagine space-time as a vast rubber sheet, stretched tight. Place a bowling ball in the center, and it creates a depression. Now roll a marble around the edge of that depression. The marble isn't being pulled by some invisible string. It's simply following the curve of the sheet. It wants to go straight, but straight in curved space becomes a circle. This is how planets orbit the sun, how moons orbit planets, how galaxies wheel through the cosmos. Everything is falling along the curves of space-time, and those curves guide the fall into endless, beautiful circles. But perhaps you're wondering about those subtle forces I mentioned, the ones that do cause real changes over time. Let me tell you about one of the most poetic of these, the Poynting-Robertson effect. Every particle of light that streams out from the sun carries a tiny bit of momentum. When this light hits a planet or an asteroid or even a grain of dust, it gives it the gentlest of pushes. For large objects like planets, this push is almost nothing, like trying to move a mountain by blowing on it. But for small particles of dust, over millions of years, this gentle breath of light can actually cause them to spiral slowly inward, toward the sun. There's something beautiful about this, isn't there? The very light that warms our world, that makes life possible, is also gently, almost imperceptibly, affecting our orbit. But before you worry, let me reassure you. For Earth, this effect is so small that it would take longer than the current age of the universe to produce any noticeable change. We're far too massive, our momentum far too great to be significantly affected by the gentle pressure of sunlight. Another force at work is even more subtle: gravitational waves. When massive objects accelerate through space, they create ripples in space-time itself, waves that carry energy away from the system. Einstein predicted these waves a century ago, but they're so faint that it took until 2015 for scientists to detect them directly, using instruments so sensitive they can measure distances smaller than the width of a proton. For binary systems, where two massive objects orbit very close together, these waves can cause immeasurable spiral over time. But for our solar system, with its vast distances and relatively small masses, the effect is almost infinitely tiny. The Earth loses less energy to gravitational waves in a year than you use to lift this thought into your consciousness. Yet another subtle player in this cosmic dance is the solar wind. that stream of charged particles that flows continuously from the sun's surface. This wind exerts a pressure on everything in the solar system, a pressure that varies with solar activity, waxing and waning over the sun's 11-year cycle. During solar storms, this wind can gust and blow, causing auroras to dance in our polar skies and satellites to feel an extra drag. But again, for planets, the effect is minimal. We're like boulders in a gentle breeze, barely noticing the wind that would send a feather tumbling. There's also something called the Yarkovsky effect, named after the Russian engineer who first described it. When an asteroid rotates, the side that has been heated by the sun slowly turns away, radiating that heat back into space. But because it takes time for the surface to heat up and cool down, the hottest part of the asteroid isn't the point directly facing the sun, but rather a spot that's rotated slightly past noon, so to speak. This means the thermal radiation isn't perfectly balanced, creating a tiny thrust that can, over millions of years, alter an asteroid's orbit. For planets, this effect exists but is even tinier than tiny, lost in the noise of other forces. All of these effects, the pressure of light, the pull of gravitational waves, the push of solar wind, the asymmetry of thermal radiation, they're all real, all measurable with our most sensitive instruments. But they're also all incredibly, almost impossibly small when it comes to planets. It's like trying to push a cruise ship with a feather, or alter the course of a river with a teaspoon. The forces exist, but they're overwhelmed by the sheer momentum of these massive worlds. And yet, there's something profound in knowing that these forces exist at all. They remind us that nothing in the universe is truly isolated, that everything influences everything else, even if only by the tiniest amount. Every photon of light that leaves the sun and strikes the Earth links us to our star. Every gravitational wave that passes through our planet connects us to distant colliding black holes. We're part of a vast web of interactions, a cosmic symphony where every object plays its part, no matter how quiet its voice. This is why the question of whether planets are falling into the sun is so beautifully complex. In one sense, yes, we're always falling, following the curved path that gravity creates through space-time. But in another sense, we're in perfect balance, our sideways motion exactly matching our inward fall, creating a stable orbit that can last for billions of years. And in yet another sense, we're subject to countless tiny forces that do cause real, measurable changes over time, even if those changes are so slow that they make geological time seem fast by comparison. Scientists have spent centuries refining our understanding of these orbital dynamics. They've developed mathematical frameworks of stunning beauty and precision, equations that can predict the position of planets thousands of years into the future or past. They've built computers that can simulate the gravitational interactions of hundreds of thousands of objects simultaneously, tracking how orbits evolve over cosmic time. And what they've found is that our solar system, despite all these subtle forces and interactions, is remarkably stable. This stability isn't absolute, of course. Over truly vast timescales, measured in hundreds of millions or billions of years, chaotic interactions can accumulate. There's a tiny chance that Mercury's orbit could become unstable in the distant future, or that gravitational perturbations from passing stars could affect the outer planets. But these are possibilities so remote, timescales so vast, that they're more like abstract mathematical curiosities than real concerns. For all practical purposes, for all the time that Earth has existed and will exist as a living world, our orbit is safe. In fact, if anything, the Earth is slowly drifting away from the Sun rather than toward it. You see, the Sun is slowly losing mass. Every second, it converts about 4 million tons of matter into pure energy through nuclear fusion, energy that streams out as light and heat. Additionally, the solar wind carries away about 1 million tons of material per second. Over the lifetime of the Sun, this adds up to a significant amount of mass loss. And as the Sun becomes lighter, its gravitational grip weakens ever so slightly, allowing planets to drift outward. The rate of this drift is almost incomprehensibly slow. Earth moves away from the Sun by about 1.5 centimeters per year due to solar mass loss. That's about the rate at which your fingernails grow. In the billion years since complex life first appeared on Earth, our planet has drifted outward by only about 15,000 kilometers, a tiny fraction of our 150 million kilometer distance from the Sun. It would take about 10 billion years for this effect to increase our orbital distance by even 1%. This gentle outward drift is actually a cosmic mercy. As the sun ages, it's slowly growing brighter, increasing its energy output by about 1% every 100 million years. This gradual brightening would eventually make Earth too hot for life as we know it. But our slow outward drift partially compensates for this, giving our planet perhaps an extra few 100 million years of habitability. It's as if the universe has built in a subtle mechanism to extend the time that worlds like ours can harbour life. But let's return to that central paradox, the idea that we're falling and not falling at the same time. This isn't just a quirk of orbital mechanics, it's a fundamental feature of how gravity works in our universe. Einstein showed us that there's no difference between floating in space and falling freely in a gravitational field. If you were in a windowless box falling toward Earth, you would feel weightless, exactly as if you were floating in deep space, far from any gravitational influence. This equivalence is so fundamental that physicists call it the equivalence principle, and it's one of the cornerstones of our understanding of gravity. This is why astronauts in the International Space Station float. They're not beyond Earth's gravity. In fact, the gravitational force at their altitude is about 90% of what it is at Earth's surface. But they're in free fall, falling around the Earth just like the station itself, and so they experience weightlessness. They're falling every moment of every day, but because they're moving sideways fast enough, they keep missing the Earth. They're in exactly the same situation as our planet orbiting the Sun, just on a smaller, faster scale. There's a beautiful thought experiment that illustrates this. Imagine you could drill a tunnel straight through the Earth from one side to the other. If you dropped a ball into this tunnel, it would fall toward the center, accelerating as it went. But it wouldn't stop at the center. Its momentum would carry it through to the other side, where it would slow down, stop, and fall back again. If there were no air resistance, the ball would oscillate back and forth forever, taking about 84 minutes to make a complete round trip. Now imagine instead of a straight tunnel, you have a circular tunnel running around the Earth just beneath the surface. A ball moving through this tunnel at the right speed would orbit underground, taking, you guessed it, about 84 minutes to complete one orbit. This is the same time it takes for any object to orbit just above Earth's surface, whether it's going through the planet, around it, or in any elliptical path that grazes the surface. This deep connection between falling and orbiting reveals something profound about the nature of gravity and motion. Every orbit is a fall, and every fall, if properly directed, can become an orbit. The planets aren't defying gravity. They're expressing it in its purest form. They're showing us that gravity doesn't just pull things down, it shapes the paths that objects follow through space and time. And this brings us to a rather wonderful realization. You, lying there in your bed, are also in orbit around the Sun. You're not just on a planet that orbits the Sun, you personally are tracing out your own path through space, a path that spirals through the cosmos as Earth rotates and orbits, as the Sun moves through the galaxy, as the galaxy moves through the universe. You're falling through space-time along a complex, beautiful trajectory that will never exactly repeat. Every moment of your life corresponds to a unique position in the cosmos, a point in space and time that has never been occupied before, and will never be occupied again. Consider the scale of the journey you're on right now, even as you lie still. Earth orbits the Sun at about 30 kilometers per second. That means in the time it takes you to draw a single breath, you've traveled hundreds of kilometers through space. By the time you wake tomorrow, you'll be 2.5 million kilometers from where you are now. And yet, because everything around you, your room, your city, the air you breathe, is moving with you, this tremendous journey feels like perfect stillness. This is the paradox of cosmic motion. The faster you're moving, the less you feel it. Earth spins at the equator at over 1,600 kilometers per hour, but we don't feel dizzy. We orbit the Sun at over 100,000 kilometers per hour, but we don't feel the acceleration. The entire solar system moves through the galaxy at over 700,000 kilometers per hour, and the galaxy itself hurtles through space at millions of kilometers per hour. But to us, the night is still and quiet. We're like passengers on the smoothest, most perfect vehicle ever created, a 4.5 billion-year-old spaceship that carries us through the cosmos with such grace that we can balance a pencil on its point, or build card houses that stand for hours. The reason we can sleep peacefully, the reason a glass of water sits calmly on your nightstand, The reason the atmosphere doesn't get left behind as Earth races through space is that we're all falling together. Every atom of Earth, every molecule of air, every drop of water in the oceans is following the same curved path through space-time. We're like a school of fish moving as one through the cosmic ocean, each individual following the same current, maintaining our relative positions even as we traverse vast distances. And perhaps this is why the idea of planets falling into the sun feels both true and untrue at the same time. It's true in the sense that we're always accelerating toward the sun, always feeling its gravitational influence, always curving our path in response to its presence. But it's untrue in the sense that this fall is stable, balanced, sustainable. We're not falling in the way a dropped object falls to the ground. We're falling in the way a river flows to the sea, continuously, purposefully, following the shape of the landscape but never running out of water to flow. The ancient Greeks had two words for time, chronos and kairos. Chronos is mechanical time, the time of clocks and calendars, the time that marches forward second by second. Kairos is the right time, the perfect moment, the time when everything comes together. Our orbit around the sun expresses both kinds of time. It's chronos in its regularity, its predictability, its mechanical precision, but it's also kairos in its perfection, its balance, its ability to create just the right conditions for life to flourish. Think about how precise our orbit needs to be for life to exist. If we were just 5% closer to the sun, Earth would be like Venus, with a runaway greenhouse effect and surface temperatures hot enough to melt lead. If we were just 10% farther away, we'd be frozen solid, with even the oceans turned to ice. Our orbit places us in what scientists call the habitable zone, the narrow range of distances where liquid water can exist on a planet's surface. And we've been in this zone for billions of years, our orbit stable enough to allow life to evolve from simple single cells to the complex biosphere we see today. This stability is even more remarkable when you consider all the things that could have gone wrong. In the early solar system, planets migrated dramatically, with Jupiter and Saturn moving inward and then outward again, their gravitational influence reshaping the orbits of smaller worlds. Many planets that formed in the early solar system were ejected entirely, flung into interstellar space by gravitational encounters. Others collided and merged like the Mars-sized body that struck Earth and created the Moon. Through all this chaos, Earth found a stable orbit and kept it, like a dancer finding the perfect rhythm amidst the swirling chaos of a cosmic ballet. The Moon itself plays a crucial role in maintaining Earth's stability. Its gravitational pull creates tides, yes, but it also helps stabilize Earth's axial tilt, preventing the wild swings that would otherwise occur due to the gravitational influence of other planets. Without the Moon, Earth's axis might wobble chaotically over millions of years, causing dramatic climate changes that would make ice ages look mild by comparison. But with the Moon as our celestial companion, our tilt remains relatively stable, varying by only a couple of degrees over tens of thousands of years. The Moon is also slowly spiraling away from Earth, moving outward by about 3.8 centimeters per year due to tidal interactions. This is the same effect that has gradually slowed Earth's rotation, lengthening our days from about 6 hours when the Moon first formed to the 24 hours we experience today. In the distant future, billions of years from now, Earth and Moon will become tidally locked, with the same faces always pointing toward each other, and a day will last as long as a month. But this is a change so slow, so gradual, that life has had plenty of time to adapt to the gradually lengthening days. These orbital dynamics create rhythms that permeate every aspect of life on Earth. The daily cycle of light and dark drives circadian rhythms in almost every living thing. The annual orbit around the Sun creates seasons that trigger migrations, hibernations, breeding cycles, and the growth patterns of plants. Even the longer cycles, the precession of Earth's axis every 26,000 years, the variations in orbital eccentricity every 100,000 years, leave their marks in the geological record, in the layers of rock and ice that tell the story of Earth's climate through deep time. We are creatures of these cycles, shaped by them at every level from the molecular to the behavioral. Our bodies expect the daily alternation of light and dark, the annual progression of seasons. Our cultures have built calendars and celebrations around these orbital rhythms. We plant and harvest according to Earth's position in its orbit. We navigate by the stars, which appear to move due to our orbital motion. We are, in a very real sense, orbital beings, our lives intimately connected to the fact that we're falling around the sun. And yet, for most of human history, we didn't know we were falling. To our ancestors, Earth was still and solid, the fixed centre of creation. The sun, moon, and stars appear to revolve around us, rising and setting in their appointed times. It took centuries of careful observation, mathematical innovation, and conceptual breakthroughs to realize that we're the ones in motion, that what feels like stillness is actually a headlong plunge through the cosmos, at speeds that dwarf anything in our everyday experience. This discovery, this shift from a stationary Earth to a moving one, was perhaps the greatest conceptual revolution in human history. It required us to trust mathematics and observation over our direct sensory experience. It asked us to believe that we could be moving at tremendous speeds without feeling it, that up and down were relative concepts, that the Earth could be round and spinning without us falling off. It was a leap of faith backed by evidence, a willingness to see beyond the obvious to the true. And now, centuries later, we've not only accepted this reality but built our entire technological civilization around it. Our satellites orbit Earth using the same principles that keep Earth orbiting the Sun. Our spacecraft navigate using orbital mechanics, using gravity assists to gain speed, entering orbit around other worlds, even landing on comets and asteroids that are themselves in complex orbits around the Sun. We've become masters of falling, turning what might seem like helplessness, being at the mercy of gravity, into a tool for exploration. Every spacecraft we've ever launched has been an exercise in precision falling. To reach Mars, we don't point a rocket at where Mars is now and fire. Instead, we calculate where Mars will be months from now and launch our spacecraft into an orbit that will intersect with Mars at exactly the right time. The spacecraft falls around the Sun in an elliptical path, using the Sun's gravity to carry it across hundreds of millions of kilometers of space. When it arrives at Mars, it has to adjust its fall again, using rockets or atmospheric braking to fall around Mars instead of past it. The Voyager spacecraft, launched in the 1970s, used the gravity of Jupiter and Saturn to change their falls, stealing a bit of those planets' orbital energy to fling themselves into the outer solar system and beyond. They're still falling, but now they're falling away from the Sun, climbing up out of the Sun's gravitational well with enough speed that they'll never fall back. They've achieved escape velocity, breaking free from the closed loops of orbital motion to trace open paths into interstellar space. But even as they escape the Sun's gravity, the Voyagers are still falling. They're falling through the galaxy, following curved paths influenced by the gravitational pull of hundreds of billions of stars. They're falling through the universe, participating in the cosmic expansion that carries all galaxies away from each other. There is no place in the universe where you can truly stop falling, no reference frame that is absolutely at rest. Everything is falling relative to something else, and that universal fall is what we call the flow of time itself. Einstein showed us that gravity and acceleration are indistinguishable, that falling and floating are the same experience, but he also showed us something even more profound, that gravity is not a force at all, but the curvature of space-time caused by mass and energy. When we fall, we're not being pulled by some invisible string. We're following the straightest possible path through curved space-time, like water flowing down a hillside, finding the path of least resistance through the landscape of reality. This means that when Earth orbits the Sun, it's not fighting against gravity or defying it. It's doing exactly what gravity tells it to do, following the natural grooves and channels that mass creates in the fabric of space-time. It's like a marble rolling around the inside of a bowl, not because something is pushing it in circles, but because the shape of the bowl guides its motion. The Sun has created a bowl-shaped depression in space-time, and Earth rolls around the sides of that bowl, never reaching the bottom because its sideways motion keeps it at a constant height. But unlike a real marble in a real bowl, Earth doesn't slow down due to friction. Space is the most perfect vacuum we know, offering essentially no resistance to motion. Once set in motion, objects in space continue moving forever, unless acted upon by some force. This is Newton's first law, the law of inertia, and it's why Earth has been able to maintain its orbit for billions of years without slowing down or speeding up significantly. We're perpetual motion machines, not because we've violated the laws of thermodynamics, but because there's nothing to steal our energy away. Well, almost nothing. As I mentioned earlier, there are those tiny forces, gravitational waves, tidal interactions, the pressure of sunlight, that do cause infinitesimal changes over cosmic time. But these forces are so weak that they're like trying to stop a freight train with a feather. The Earth has tremendous angular momentum, the rotational equivalent of linear momentum, and changing that angular momentum requires enormous forces acting over vast periods of time. To put this in perspective, the Earth's orbital angular momentum is about 2.7 or sus 10 to 40 kilogram meters squared per second. That's a 27 followed by 39 zeros. The total energy of Earth's orbital motion is about 2.7 as 10 to 33 joules. For comparison, all of human civilization uses about 5x 10 to 20 joules of energy per year. Earth's orbital energy could power our entire civilization at current rates for billions of times longer than the universe has existed. This is the scale of the motion we're talking about, the vastness of the fall that we don't notice, and yet despite these enormous numbers, the physics is simple. It's the same physics that governs a ball thrown in the air or a pendulum swinging back and forth. The mathematics that describes Earth's orbit could be understood by a bright high school student. The principles are elegant, beautiful, almost poetic in their simplicity. Mass attracts mass. Objects in motion stay in motion. Every action has an equal and opposite reaction. From these simple rules emerges the complex dance of the cosmos, the intricate choreography that keeps worlds in their places and allows life to flourish. As you lie there, perhaps you can feel it now, not the motion itself, which is too smooth to perceive, but the knowledge of it, the understanding that you're part of this cosmic dance. You're not a passive observer of the universe, you're an active participant tracing your own unique path through space and time. Every breath you take, every heartbeat, every thought that passes through your mind happens at a specific point in the cosmos that will never be repeated. You're not just in the universe, you're of it, made from star stuff, held together by the same forces that hold planets in their orbits. The calcium in your bones, the iron in your blood, the carbon in your DNA. All of these atoms were forged in the hearts of dying stars billions of years ago. They've been falling through space ever since, pulled by gravity into clouds of gas and dust, condensing into new stars and planets, eventually becoming part of Earth, part of life, part of you. You're made of cosmic travelers, atoms that have been falling through space for eons, and you're continuing their journey, carrying them along Earth's orbit around the Sun. This is the deeper truth about our fall around the Sun. It connects us to everything. The same gravity that keeps Earth in orbit also holds galaxies together, forms stars and planets, creates the tides that may have helped life begin in primeval tide pools. We're not separate from the cosmos looking up at it from outside. We're embedded in it, woven into its fabric, shaped by its forces. The fall that we don't notice is the fall that makes our existence possible, and perhaps this is why contemplating our cosmic motion can be so soothing, so conducive to sleep. It reminds us that we're held, that we're safe, that forces far greater than ourselves are maintaining the stability that allows us to rest. We don't have to hold ourselves in orbit. Gravity does that for us. We don't have to push Earth along its path. Momentum takes care of that. We can let go, relax, trust in the physics that has kept our world safe for billions of years and will continue to do so for billions more. As your eyes grow heavy, as your breathing deepens and slows, remember that you're falling. You're falling around the Sun at 30 kilometers per second, and that fall is what creates the stability you feel as stillness. You're falling through the galaxy at hundreds of kilometers per second, carried along by the Sun in its own vast orbit. You're falling through the universe, participating in the cosmic expansion that began with the Big Bang and continues to this day. And all of these falls, all of these motions are perfectly balanced, perfectly stable, creating the conditions for rest, for peace, for sleep. The planets will continue their dance while you dream. Mercury will race around its tight orbit, completing another circuit in just 88 days. Venus will turn slowly backward, its day longer than its year. Mars will trace its elliptical path, sometimes approaching Earth, sometimes receding. Jupiter and Saturn will proceed majestically through their longer orbits, shepherding asteroids and comets, protecting the inner solar system from impacts. Uranus and Neptune will continue their slow progressions through the outer darkness, taking centuries to complete single orbits. And Earth? our beautiful blue marble, will continue its perfect fall around the sun, carrying you safely through another night, another day, another year. The fall that we don't notice will continue, as it has for billions of years, as it will for billions more. You can rest in that knowledge, sleep in that certainty, dream in that cosmic embrace. You're falling, we're all falling, and that fall is what keeps us safe, what makes life possible, what connects us to the grand story of the universe. In the morning, when sunlight streams through your window, remember that those photons have travelled 150 million kilometres to reach you, crossing the void in just 8 minutes. They're proof of our connection to the sun, evidence of the orbit that we don't feel, but that shapes every aspect of our existence. The warmth on your face is the gentle touch of the star we're falling around, the star that we'll never reach because we're moving too far sideways, missing it forever in the most beautiful way possible. Now we begin to understand scale, the true vastness of time and space that makes our perpetual fall possible. If we could somehow compress the entire history of our solar system into a single day, the scale of our existence would become breathtakingly clear. Imagine the clock striking midnight at the moment of the solar system's birth, 4.6 billion years ago. In this compressed timeline, each second represents about 53,000 years, each minute holds 3.2 million years, and each hour contains nearly 200 million years of cosmic history. At the stroke of midnight, there is no sun, no planets, just a vast cloud of gas and dust, slowly rotating, slowly contracting under its own gravity. By 12:01 a.m., just 1 minute into our cosmic day, the cloud has begun to flatten into a disk, with a dense concentration at its centre that will become our sun. The temperature rises as gravitational potential energy converts to heat. Particles collide, stick together, begin forming the first tiny grains of solid matter in a universe that has been mostly gas until now. By 12:30 a.m., the sun ignites. Nuclear fusion begins in its core as temperatures and pressures reach the critical threshold. A star is born, and its light begins streaming outward, pushing against the surrounding gas and dust. The solar wind begins to blow, clearing out the inner solar system, creating the relatively empty space through which planets will soon orbit. This is the first half hour of our compressed day, and already 380 million years have passed. The planets begin forming almost immediately after the sun's ignition. In the inner solar system, where temperatures are high, only rocky materials can condense into solid form. Small grains collide and stick together, forming pebbles, then boulders, then mountain-sized bodies called planetesimals. By 1 a.m., just 1 hour into our day, Earth has grown to perhaps half its current size through this process of accretion. Every impact adds mass and energy, keeping the young planet molten, a ball of liquid rock falling around the newborn sun. At approximately 1:30 a.m., a Mars-sized body called Theia collides with Earth in a cataclysmic impact that liquefies both bodies and throws vast amounts of debris into orbit. Within minutes of cosmic time, perhaps just a few thousand years, this debris coalesces into the Moon. It's much closer to Earth than it is today, looming enormous in the sky, raising tides in the molten rock that would have dwarfed any ocean tide we see today. The Earth-Moon system has been born, and they begin their coupled fall around the Sun, a fall that continues to this moment. By 2 a.m., Earth has cooled enough for the first solid crust to form, though it's constantly broken and reformed by continued impacts and volcanic activity. The Moon is still very close, perhaps only 20,000 kilometres away compared to its current distance of 384,000 kilometres. A day on Earth lasts only about 6 hours. The planet spins rapidly, and the close Moon raises enormous tides that help slow this rotation, gradually transferring angular momentum from Earth's spin to the Moon's orbit, causing the Moon to slowly spiral outward. Water begins to condense from the atmosphere around 2:30 a.m. The first oceans form, though they're hot and acidic, nothing like the blue waters we know today. But water is patient, and it begins its work of weathering rocks, creating sediments, participating in the chemical cycles that will eventually make life possible. The Earth is still being bombarded by asteroids and comets, each impact delivering more water and organic molecules, the building blocks of life. Somewhere around 3 a.m., perhaps 3:30 a.m., life begins. We don't know exactly when or how. This is one of the great mysteries of science. But somewhere in those early oceans, perhaps in warm pools or near hydrothermal vents, molecules begin to self-replicate. The first cells appear, simple prokaryotes without nuclei, but carrying the spark of something extraordinary. The ability to reproduce, to evolve, to gradually transform a planet. For the next several hours of our compressed day, these simple cells will be the only life on Earth. By 6 a.m., a quarter of the way through our day, Earth would be unrecognizable to us. The atmosphere contains no free oxygen. It's mostly nitrogen, methane, and carbon dioxide. The sky might appear orange or brown rather than blue. The continents, such as they are, bear no resemblance to current geography. They're smaller, clustered differently, surrounded by a global ocean that covers most of the planet. And through it all, Earth continues its fall around the Sun, its orbit already stable, already reliable, already creating the rhythms that life will eventually learn to follow. At 9 a.m., something extraordinary happens. Photosynthesis evolves. Cyanobacteria begin using sunlight to split water molecules, releasing oxygen as a waste product. At first, this oxygen is immediately absorbed by iron and other elements in the oceans and atmosphere. But slowly, over the next several hours of our day, oxygen begins to accumulate. This is the Great Oxidation Event, one of the most significant changes in Earth's history. The oxygen is actually toxic to most existing life forms, causing a mass extinction. But it also opens new possibilities, new ways of extracting energy from food, new forms of life. By noon, halfway through our cosmic day, the atmosphere contains significant amounts of oxygen for the first time. The sky begins to turn blue as oxygen molecules scatter sunlight. An ozone layer forms, protecting the surface from harmful ultraviolet radiation. And somewhere in the oceans, the first eukaryotic cells appear. Cells with nuclei, the ancestors of all complex life including ourselves. These cells likely formed through symbiosis, with one cell engulfing another in a partnership that became permanent. The mitochondria in your cells, the powerhouses that provide your energy, are descendants of ancient bacteria that took up residence inside larger cells over 2 billion years ago. The afternoon of our cosmic day seems quiet, almost uneventful. From noon to about 5 p.m., life remains microscopic, single-celled, confined to the oceans. But important things are happening. Cells are experimenting with different ways of living, different metabolisms, different structures. Sexual reproduction evolves, allowing for much faster evolution by mixing genetic material from two parents. Multicellular life appears several times independently, though it remains simple, just cells sticking together, not yet specialized into different tissues and organs. Around 5:30 p.m., the first complex multicellular organisms appear. These are the Ediacaran fauna, strange soft-bodied creatures unlike anything alive today. They look like quilted mattresses, fronds and discs. They have no eyes, no mouths, no obvious way of moving. They might have absorbed nutrients directly through their skin or harbored symbiotic bacteria. They represent life's first experiment with large size, with bodies visible to the naked eye. At 6 p.m., the Cambrian explosion begins. In just a few minutes of our compressed day, about 20 million years of real time, life diversifies incredibly. Most of the major animal body plans that exist today appear during this period. Eyes evolve, allowing animals to see their world and each other. Shells and exoskeletons appear, providing protection, but also creating the first fossils that preserve well. Predation becomes common, driving an evolutionary arms race between hunters and prey. The oceans teem with trilobites, early arthropods, primitive vertebrates, and countless other forms. By 7 p.m., life ventures onto land for the first time. Simple plants and fungi establish a foothold on the barren continents. They're followed by the first land animals, arthropods like millipedes and early spiders. The continents, which have been bare rock and sand for the entire day so far, begin to turn green. Soil forms for the first time as plants break down rock and add organic matter. The terraforming of Earth's land surfaces has begun. At 8 p.m., the first forests appear. These aren't forests of flowering trees like we know today, but forests of ferns, club mosses and horsetails, some growing as tall as modern trees. The Carboniferous period begins, a time of vast swamp forests that will eventually become coal deposits. Oxygen levels rise higher than they've ever been before or since, allowing insects to grow to enormous sizes. Dragonflies with 2-foot wingspans patrol the skies. Millipedes 6 feet long crawl through the leaf litter. Around 8:30 p.m., the first reptiles evolve, animals that can lay eggs on land without returning to water. This is a crucial innovation that allows vertebrates to truly conquer the continents. By 90 p.m., the Permian period is ending with the largest mass extinction in Earth's history. Perhaps 90% of all species go extinct, possibly due to massive volcanic eruptions in what is now Siberia. Life comes closer to complete annihilation than at any other point in its history. But it survives, and in surviving opens new opportunities. At 9:15 p.m., the age of dinosaurs begins. They start small, no bigger than chickens, but they have an advantage, a more efficient breathing system and possibly warm-bloodedness that allows them to be active in a wider range of conditions. By 9:30 p.m., they've diversified into the giants we know from fossils, long-necked sauropods, fierce tyrannosaurs, horned ceratopsians. They dominate the land for the next 2 hours of our compressed day, a reign of over 150 million years. The first flowers appear around 10:30 p.m. This might seem like a small detail, but it transforms terrestrial ecosystems. Flowering plants can reproduce more efficiently than their predecessors. They form partnerships with insects, trading nectar for pollination services. They produce fruits that entice animals to spread their seeds. Within half an hour of our cosmic day, flowering plants have taken over from conifers and ferns as the dominant plant life on Earth. At 11:39 p.m., disaster strikes. An asteroid 10 kilometers wide slams into what is now the Yucatan Peninsula. The impact releases energy equivalent to billions of nuclear bombs. Earthquakes ripple around the globe. Tsunamis thousands of feet high devastate coastlines. But worst of all is the debris thrown into the atmosphere, blocking sunlight for months. Plants die, then herbivores, then carnivores. The dinosaurs, except for the branch that will become birds, go extinct. The age of mammals is about to begin. By 11:40 p.m., just 20 minutes before midnight, mammals have diversified to fill the niches left empty by the dinosaurs. Whales evolve from land-dwelling ancestors and return to the sea. Bats take to the air. Primates appear in the trees. The continents are approaching their current positions. The climate is cooling. Ice sheets beginning to form at the poles. The world is starting to look familiar. At 11:58 p.m., with just 2 minutes left in our cosmic day, the first members of the human genus appear in Africa. Homo habilis, the handyman, begins using stone tools. This is about 2.8 million years ago in real time. These early humans are still very ape-like, with small brains and bodies adapted for both tree climbing and walking upright. But they're our ancestors, beginning the journey that leads to us. At 11:59 and 30 seconds, just 30 seconds before midnight, our own species, Homo sapiens, appears. We evolve in Africa about 300,000 years ago, but we remain there for most of our history. With 15 seconds left in the day, we begin migrating out of Africa, spreading across the globe. With 10 seconds left, we invent agriculture, settling down, building the first cities. With 5 seconds left, we build the pyramids. With 2 seconds left, the Roman Empire rises and falls. In the last second of our cosmic day, all of recorded human history occurs. Every book ever written, every piece of art created, every scientific discovery made, every person who has ever lived and died in recorded history, it all happens in this final second. The invention of writing, the rise and fall of civilizations, the Renaissance, the Industrial Revolution, the Space Age, the Internet, compressed into the blink of an eye. And in the last tenth of a second, the last 5,300 years of our 4.6 billion year day, we develop astronomy. We begin to understand that we're on a planet orbiting a star. We realize we're falling around the sun. We figure out the laws of gravity and motion. We send spacecraft to other worlds. We discover that the universe is vast beyond imagination, filled with billions of galaxies, each containing billions of stars, many with their own planets falling around them just as we fall around our sun. This compressed timeline reveals something profound about our perception of planetary motion. We've only known we're orbiting the sun for about 0.0001% of the time we've actually been orbiting it. For 99.99% of Earth's journey around the sun, there was no consciousness to observe it, no mind to understand it. The fall happened anyway, reliable, consistent, following the same physical laws that govern it today. This is why we don't notice we're falling, because the timescales involve dwarf human experience so thoroughly that our motion seems like stillness. If you watched Earth's orbit from outside for a human lifetime, you would see it complete perhaps 80 circuits around the Sun, a tiny sample of the billions of orbits it has already completed. You might notice tiny variations, perturbations caused by the other planets, but you wouldn't see any systematic change in the orbit itself. It would look as constant as the mountains, as eternal as the stars. But even mountains aren't eternal, and even stars change when you watch them long enough. This is the paradox of cosmic time. Everything is in motion, everything is changing, but most of the changes happen so slowly that they're invisible to creatures like us who live for just a cosmic instant. We're like mayflies trying to understand the seasons, like bacteria trying to grasp continental drift. The universe operates on timescales that make our entire civilization seem like a single heartbeat. And yet, despite the vastness of cosmic time, we've managed to piece together this story. By looking at rocks, we can read the history of Earth. By observing other stars and planets, we can understand how our own solar system formed. By studying the laws of physics, we can project both backward and forward in time, seeing where we came from and where we're going. We may be mayflies, but we're mayflies who have figured out the seasons. The light from the sun that warms your face took 8 minutes to reach you, but the energy that created that light was generated in the sun's core perhaps 1,000,000 years ago. That's how long it takes for energy to random walk its way from the center of the sun to its surface, bouncing from atom to atom, being absorbed and re-emitted countless times. When that light finally reaches you, it's carrying information about processes that began before humans existed as a species. And the sun itself is middle-aged. It has been shining for about 4.6 billion years, and will continue shining for another 5 billion years or so. In our compressed day, the sun ignited at 12:30 a.m. and will exhaust its hydrogen fuel around 11:30 a.m. tomorrow. We're living in the sun's stable middle age, the long period when it shines steadily, allowing planets to maintain stable orbits and life to flourish. But even the sun's lifetime is brief compared to the universe itself. The Big Bang occurred about 13.8 billion years ago, meaning the universe is about 3 times older than our solar system. If we extended our compressed timeline to include the entire history of the universe, our solar system wouldn't form until 4 p.m, and humans wouldn't appear until 11:59:59.9 p.m. We are newcomers to a universe that was already old when Earth was born, and the universe will continue long after our sun dies. The smallest, coolest stars, red dwarfs, can shine for trillions of years, 1,000 times longer than our sun. The last stars won't burn out for perhaps 100 trillion years. After that, the universe will enter its dark age, when only black holes, cold stellar remnants, and sparse particles remain. But even then, motion will continue. Even in the cold darkness of the far future, objects will still orbit, still fall through space-time, following the same laws that govern Earth's fall around the sun today. This vast temporal context makes our current moment seem both insignificant and precious. We exist in a tiny window of cosmic time when stars shine, planets orbit, and life is possible. We're riding a wave that began with the Big Bang and will continue until the heat death of the universe. Our fall around the sun is just one small part of this larger flow, but it's our part, the part we get to experience and understand. The stability of Earth's orbit over these vast timescales is remarkable, but not absolute. There are subtle changes happening all the time, changes that accumulate over millions and billions of years. The shape of Earth's orbit varies slightly, becoming more and less elliptical over a cycle of about 100,000 years. The tilt of Earth's axis wobbles between 22.1 and 24.5 degrees over a 41,000-year cycle. The direction of Earth's axis precesses like a spinning top, completing a full circuit every 26,000 years. These variations, known as Milankovitch cycles after the Serbian scientist who calculated them, affect the amount and distribution of sunlight reaching Earth. They're responsible for the ice ages that have come and gone over the past few million years. When the cycles align to reduce summer sunlight in the northern hemisphere, ice sheets can grow. When they align to increase it, the ice retreats. We're currently in an interglacial period, a warm interval between ice ages, partly because of where we are in these orbital cycles. But these cycles are gentle, predictable variations, not threats to orbital stability. Earth's distance from the Sun varies by only about 3% between its closest and farthest points. The axis tilt changes by just a few degrees. These are minor adjustments to a fundamentally stable system, like a well-tuned instrument making small variations on a theme. The basic melody, Earth's fall around the Sun, continues unchanged. Scientists have run computer simulations of the solar system's evolution over billions of years, and they've found that while the orbits of planets do change slightly due to their mutual gravitational influences, the overall architecture of the solar system remains stable. There's a mathematical concept called the Lyapunov time that describes how quickly small changes in initial conditions lead to large changes in outcomes. For the solar system, this time is about 5 million years, meaning we can't predict the exact positions of planets more than a few million years into the future or past. But we can predict the general stability of their orbits for much longer. The innermost planets, Mercury, Venus, Earth, and Mars, are in a complex gravitational dance that could, in principle, become unstable over billions of years. There's about a 1% chance that Mercury's orbit could become unstable in the next 5 billion years, potentially leading to it colliding with Venus or the Sun, or being ejected from the solar system. But Earth's orbit appears robust, protected by its relatively large mass and favourable position. The giant planets, Jupiter, Saturn, Uranus, and Neptune, are even more stable. Their massive gravitational fields have cleared out their orbital neighbourhoods, reducing the chance of destabilising encounters. They've settled into what astronomers call mean motion resonances, where their orbital periods form simple ratios that help maintain stability. For instance, for every 2 orbits Saturn completes, Jupiter completes almost exactly 5. These resonances act like stabilising forces, preventing the planets from drifting too far from their current orbits. But perhaps the most remarkable thing about Earth's orbital stability is how it has persisted through dramatic changes in the solar system's configuration. Early in the solar system's history, the giant planets likely migrated significantly. Jupiter may have moved inward and then back outward, a journey that would have dramatically affected the orbits of smaller bodies. This migration, known as the Grand Tack model, could explain many features of our solar system, including the relatively small size of Mars and the structure of the asteroid belt. There was also likely a period of late heavy bombardment about 3.9 billion years ago, when the migration of the outer planets destabilized populations of asteroids and comets, sending them careening through the inner solar system. Earth was pummeled by impacts during this period, as evidenced by the cratered surfaces of the Moon and other airless bodies. Yet through all this chaos, Earth maintained its orbit, continuing its fall around the Sun. This persistence reveals something fundamental about orbital mechanics. Once established, orbits are remarkably difficult to disrupt. It takes a close encounter with a body of comparable mass to significantly change a planet's orbit. For Earth, this would mean a close pass by something at least the size of Mars, and there simply aren't any objects that large wandering through the inner solar system. The planets have long since settled into their own stable orbits, and the asteroids and comets are too small to matter. Even when catastrophic events do occur, orbits often survive. The impact that created the Moon was energetic enough to melt both Earth and the impactor, yet Earth remained in a stable orbit around the Sun. The asteroid impact that killed the dinosaurs released enormous energy, but it changed Earth's orbit by an imperceptible amount. These events remind us that while life on Earth's surface may be fragile, the planet's orbit is robust. This orbital stability has profound implications for life. Evolution requires time, vast amounts of time, to produce complex organisms. If Earth's orbit were unstable, if we regularly wandered too close to or too far from the Sun, life as we know it could never have evolved. The billions of years of stable conditions provided by our steady fall around the Sun gave life the time it needed to experiment, to fail, to try again, to eventually produce the incredible diversity we see today. Consider photosynthesis, the process that powers most life on Earth. It evolved to use sunlight of a specific intensity and spectrum, the light provided by our Sun at our orbital distance. If Earth's orbit varied significantly, photosynthesis might not work reliably. Plants would have to constantly adapt to changing light conditions, and the entire food web built on photosynthesis would be unstable. But because our orbit is stable, because the sunlight reaching Earth is consistent from year to year and millennium to millennium, photosynthesis could evolve and optimize, becoming the incredibly efficient process it is today. The same is true for countless other biological processes. The circadian rhythms that regulate sleep and waking evolved in response to the reliable 24-hour day-night cycle created by Earth's rotation. The seasonal behaviors of plants and animals, migration, hibernation, flowering, mating, evolved in response to the predictable annual cycle created by Earth's orbit. If these cycles were irregular or unpredictable, life would have evolved very differently, if at all. Our stable orbit has also allowed for the development of climate systems that, while variable, remain within bounds compatible with life. The water cycle, the carbon cycle, the circulation of atmosphere and oceans, all of these depend on consistent energy input from the Sun. If Earth's orbit were highly elliptical, we would experience extreme seasons that might prevent the establishment of stable ecosystems. If our orbit was slowly decaying, the gradual heating would eventually boil away the oceans. If it were expanding, the gradual cooling would freeze the planet solid. Instead, we have a nearly circular orbit that keeps solar input nearly constant, allowing for the development of complex, stable climate systems. Yes, there are ice ages and warm periods, driven by those subtle Milankovitch cycles I mentioned, but these changes are gradual enough for life to adapt, to migrate, to evolve. They're variations on a theme, not a complete rewriting of the song. The measurement of Earth's orbit has become incredibly precise in recent decades. We can now track our position relative to the Sun with an accuracy of meters, even though we're 150 million kilometers away. This is accomplished through a variety of techniques, including radar ranging to planets, laser ranging to the Moon, and precise timing of spacecraft communications. Every measurement confirms the stability of our fall around the Sun. One of the most elegant confirmations comes from pulsar timing. Pulsars are rapidly rotating neutron stars that emit regular pulses of radiation like cosmic lighthouses. Some pulsars are so regular that they rival atomic clocks in precision. As Earth orbits the Sun, our changing position causes tiny variations in when we receive these pulses. They arrive slightly early when we're moving toward the pulsar, slightly late when we're moving away. By carefully timing these variations, astronomers can map Earth's orbit with extraordinary precision. Another confirmation comes from the cosmic microwave background, the afterglow of the Big Bang. As Earth orbits the Sun, our motion through space causes a tiny Doppler shift in this background radiation. It appears slightly warmer in the direction we're moving, slightly cooler behind us. This effect, called the dipole anisotropy, gives us an independent measurement of our orbital velocity. And once again, it confirms that we're falling around the Sun at exactly the speed and distance that centuries of other observations have told us. Even gravitational wave detectors, the most sensitive instruments ever built, confirm our orbital motion. These detectors can measure changes in distance smaller than the width of a proton, and they have to account for Earth's orbital motion when analysing their data. The gravitational waves from distant colliding black holes arrive at slightly different times at different detectors due to Earth's motion, and this difference must be precisely calculated to locate the source of the waves. All of these measurements, using completely different physics and techniques, tell the same story. Earth is in a stable, nearly circular orbit around the Sun, falling continuously but never getting closer, held in perfect balance by the interplay of gravity and momentum. It's a fall that has continued for billions of years and will continue for billions more, a fall so smooth and consistent that we perceive it as stillness. As you drift towards sleep, consider this temporal vastness, this stability that stretches from the deep past into the far future. You are participating in a motion that began before life existed and will continue long after the last life on Earth has vanished. You're riding a wave that connects you to every creature that has ever lived on this planet, every plant that has ever grown, every raindrop that has ever fallen. They all shared this same orbit, this same fall around the Sun, and yet despite the vastness of these timescales, despite the enormous energies and distances involved, the physics is simple enough for us to understand. We can calculate orbits, predict eclipses, send spacecraft to distant worlds. We've taken the mystery of the heavens and made it comprehensible without losing any of its wonder. If anything, understanding how it all works makes it more wondrous, not less. The next time you see the Sun, remember that you're falling toward it at this very moment, accelerating at about 6 millimeters per second squared, But you're also moving sideways at 30 kilometers per second, fast enough to travel around Earth's equator in just 22 minutes. These two motions combine to create your orbit, your eternal fall that never ends. You're a cosmic dancer, tracing a path through space that's uniquely yours, even as you follow the same general orbit as everyone else on Earth. And now, as we prepare to explore the deeper mechanics of this dance, the subtle forces and gentle perturbations that shape our fall, let your mind rest in the knowledge that you're held by forces that have been reliable for eons. The same gravity that pulls you gently into your bed pulls Earth toward the Sun. The same momentum that carries your thoughts forward carries Earth along its orbit. You're not separate from these cosmic forces. You're an expression of them, a temporary arrangement of matter and energy participating in the eternal dance of the cosmos. The story continues, the fall continues, and you continue with it, safe in the embrace of physics, held by the same forces that hold the stars in their courses and the galaxies in their majestic rotations. Sleep is coming, carried on the same wave that carries Earth around the Sun, and there's nothing you need to do but let yourself fall into it, knowing that you'll wake tomorrow still falling, still safe, still part of this beautiful eternal dance around our star. Now we turn to one of the most beautiful insights in all of physics, an understanding that transforms our conception of falling from something violent and dangerous into something gentle and eternal. Picture, if you will, Newton's famous thought experiment, but let's explore it with the slow, contemplative attention it deserves. Imagine standing on a mountain so tall that its peak rises above Earth's atmosphere, reaching into the vacuum of space where there's no air resistance to slow things down. From this impossible height, you have a cannon, and you're about to conduct an experiment that will reveal the secret of orbital motion. You load the cannon with a cannonball and fire it horizontally, parallel to Earth's surface far below. If you fire the cannon with a modest amount of gunpowder, the cannonball arcs through space and falls back to Earth some distance away. It traces a parabola, that familiar curve of thrown objects, rising briefly from the momentum of its launch, then falling as gravity overcomes its upward motion. The ball might travel a few kilometers before crashing back to the ground. This is the kind of falling we're familiar with, the falling that ends with an impact. Now you add more gunpowder and fire again. The cannonball travels faster, farther, its arc is longer, more stretched out. It might travel tens of kilometers, hundreds of kilometers before returning to Earth. But it still falls, still impacts, still ends its journey. The trajectory is longer but fundamentally the same, a path that intersects with Earth's surface. But here's where Newton's genius reveals itself. He realized that Earth's surface isn't flat, it's curved. As the cannonball travels horizontally, the ground beneath it curves away. For every 8 kilometers the cannonball travels horizontally, Earth's surface curves down by about 5 meters due to the planet's spherical shape. This might seem like a tiny detail, but it changes everything. You add still more gunpowder, firing the cannonball even faster. Now it travels so far that Earth's curvature becomes significant. The cannonball is still falling toward Earth at the same rate. Gravity hasn't weakened. But Earth's surface is curving away from the cannonball's path. The ball falls 5 meters in the first second, but Earth's surface has also curved away by some amount. The net result is that the cannonball doesn't get much closer to the ground. And now comes the magical moment, the speed at which everything changes. You fire the cannon with exactly the right amount of force, about 7.9 kilometers per second for an object at Earth's surface. At this speed, something extraordinary happens. The cannonball falls toward Earth at exactly the same rate that Earth's surface curves away from it. For every meter the ball falls, the surface drops away by a meter. The cannonball is falling, always falling, but it never gets closer to the ground. This is orbit. This is what every satellite, every space station, every moon, and every planet is doing. They're falling toward the body they orbit, but moving sideways fast enough that they miss. They're in an eternal state of missing, falling past their target rather than into it. It's not that gravity has been overcome or defeated. Gravity is still there, still pulling, still causing the fall, but the fall has been transformed from a straight line into a circle, or more generally, an ellipse. Think about what this means for Earth and the Sun. Earth is Newton's cannonball, fired long ago when the solar system formed, given its sideways velocity by the conservation of angular momentum as the primordial cloud collapsed. Earth falls toward the Sun at every moment, accelerating toward it, curving its path inward. But Earth is also moving sideways at 30 kilometers per second, fast enough that the Sun's surface, or rather the point Earth would need to reach to collide with the Sun, curves away in space-time. Einstein deepened this understanding in a way that's even more beautiful. In his general theory of relativity, gravity isn't a force at all. It's the curvature of space-time caused by mass and energy. Massive objects like the Sun don't pull on planets. They bend the fabric of space-time, creating valleys and curves that guide motion. Imagine space-time as a vast, flexible fabric, like a rubber sheet stretched tight. When you place a massive object like the Sun on this fabric, it creates a depression, a warping of the surface. Now, if you roll a marble along this fabric, it will curve toward the depression. Not because the massive object is pulling on it with invisible strings, but because the marble is following the straightest possible path through curved space. But here's the subtle beauty. If you give the marble exactly the right sideways velocity, it will roll around the depression without falling in. It's following the curvature of space, tracing what's called a geodesic, the equivalent of a straight line in curved space-time. The marble thinks it's going straight, but straight and curved space becomes a circle or ellipse. This is what Earth is doing around the Sun. We're following the straightest possible path through the curved space-time that the Sun creates. We're not being pulled or pushed. We're simply following the geometry of space itself. We're like a train on invisible tracks, tracks carved into the fabric of reality by the Sun's mass. We have no choice but to follow these tracks, and following them means orbiting, means falling forever without ever arriving. The mathematics of this is beautiful in its simplicity. The curvature of space-time around a massive object is described by Einstein's field equations, which relate the geometry of space to the energy and momentum within it. These equations tell us that mass and energy curve space-time, and the curvature of space-time tells matter how to move. As physicist John Wheeler eloquently put it, matter tells space-time how to curve, and space-time tells matter how to move. For weak gravitational fields like those in our solar system, Einstein's equations reduce to Newton's law of gravity with tiny corrections. The orbit of Earth around the Sun is 99.999% Newtonian, with general relativity adding subtle refinements. These refinements are measurable. They show up in the precession of Mercury's orbit, in the bending of light near the Sun, in the time delay of signals passing through the solar system, but they don't change the fundamental picture of planets falling around their stars. One of the most profound aspects of Einstein's insight is the equivalence principle, the idea that being in free fall is indistinguishable from floating in empty space. If you were in a windowless box falling toward Earth, you would feel weightless, exactly as if you were floating far from any gravitational influence. This is because you and the box are falling together, accelerating at the same rate. There's no relative motion between you and your immediate surroundings, so you feel no force. This is why astronauts float in the International Space Station. They're not beyond Earth's gravity. At their altitude of about 400 kilometers, gravity is still about 90% as strong as at Earth's surface. But they're in free fall, falling around Earth just like their spacecraft, so they experience weightlessness. They're Newton's cannonball made real, fired horizontally with enough velocity to miss Earth continuously. The same principle applies to Earth orbiting the Sun. We're in free fall around the Sun, and if we could somehow eliminate all the other forces we experience, Earth's gravity, air resistance, friction, we would feel weightless with respect to the Sun. We don't notice our fall because everything around us is falling at the same rate. The ground beneath our feet, the air we breathe, the water in the oceans, it's all falling toward the Sun together, maintaining the same relative positions. This is why a glass of water sits calmly on your nightstand despite Earth's tremendous velocity through space. The water, the glass, the nightstand, and Earth itself are all following the same curved path through space-time. They're like passengers on the same train, moving together at high speed but stationary relative to each other. The water doesn't slosh toward the Sun because it's falling toward the Sun at exactly the same rate as its container. But let's explore the subtle forces that do create tiny deviations from this perfect free fall. These are called tidal forces, and they arise because gravity varies with distance. The side of Earth facing the Sun experiences slightly stronger gravity than the center of Earth, which in turn experiences stronger gravity than the far side. These differences are tiny. The Sun's gravity varies by only about 0.06% across Earth's diameter, but they're real, and they have measurable effects. Tidal forces from the Sun cause Earth to bulge slightly, stretching it into a very subtle oblate shape with the long axis pointing toward the Sun. The solid Earth deforms by only a few centimeters, but the oceans, being liquid, respond more dramatically. The Sun contributes about 1/3 of the tidal effect we see in the oceans, with the Moon, despite being much smaller but much closer, contributing the other 2/3. These tidal bulges don't point exactly at the Sun because Earth is rotating. Friction between the oceans and the seafloor causes the bulges to be carried slightly ahead of the Earth-Sun line. This offset means the bulges exert a tiny torque on Earth's rotation, gradually slowing it down. The same effect, but much stronger due to the Moon's proximity, is why Earth's day is gradually getting longer, increasing by about 1.7 milliseconds per century. But here's a beautiful detail. As Earth's rotation slows due to tidal friction, angular momentum must be conserved. The angular momentum lost from Earth's rotation is transferred to Earth's orbit around the Sun and the Moon's orbit around Earth. This causes both orbits to expand very slightly. Earth is moving away from the Sun by about 15 meters per century due to tidal interactions, an effect so small it's currently impossible to measure directly. There are other subtle departures from perfect free fall. The solar wind, that stream of charged particles flowing from the Sun, exerts a tiny pressure on Earth's atmosphere and magnetic field. Solar radiation pressure, the momentum carried by photons of light, pushes against Earth with a force of about 6x 10⁻⁸ newtons. That sounds like a lot, but spread over Earth's entire cross-section, it amounts to a pressure of only about 5 micropascals, billions of times weaker than atmospheric pressure. For Earth, these forces are negligible, unable to significantly affect our massive planet's orbit. But for smaller objects, they become important. Dust particles in the solar system experience something called Poynting-Robertson drag. As they orbit the Sun, they absorb sunlight from slightly ahead in their orbit due to their motion and re-radiate it in all directions. This creates a tiny drag force that causes them to spiral slowly inward. Over millions of years, this effect clears dust from the inner solar system, with the particles either falling into the Sun or being blown outward by radiation pressure if they're small enough. There's also the Yarkovsky effect, where the delayed heating and cooling of a rotating body creates a tiny thrust. As an asteroid rotates, the surface that was heated by the Sun rotates into darkness and radiates that heat into space. But because it takes time for the surface to heat and cool, the warmest part of the asteroid isn't the point directly facing the Sun, but rather a point that's rotated slightly past noon. This asymmetry in thermal radiation creates a small force that can, over millions of years, change an asteroid's orbit significantly. For Earth, the Yarkovsky effect is impossibly tiny, but it's been measured for small asteroids and is important for predicting their long-term trajectories. It's one of the many subtle forces that spacecraft navigators must consider when planning missions to asteroids and comets. Every force, no matter how small, matters when you're trying to hit a target millions of kilometers away after a journey of years. Perhaps the most exotic force affecting orbits is gravitational radiation. When massive objects accelerate, they create ripples in space-time itself, gravitational waves that carry energy away from the system. For binary systems where two massive objects orbit each other closely, this energy loss causes the orbit to decay measurably. The Hulse-Taylor binary pulsar, discovered in 1974, loses about 7 millimeters from its orbital radius each year due to gravitational radiation, causing its orbital period to decrease by 76 microseconds per year. For Earth orbiting the Sun, gravitational radiation is almost infinitely weak. We lose about 200 watts to gravitational waves, less than the power consumption of a few light bulbs. At this rate, it would take about 10^23 years for Earth's orbit to decay significantly due to gravitational radiation, a time so vast it dwarfs the current age of the universe by 13 orders of magnitude. The Sun will die long before gravitational waves have any noticeable effect on Earth's orbit. But the fact that gravitational waves exist at all is profound. It means that gravity, like electromagnetism, propagates at the speed of light. Changes in gravitational fields ripple outward through space-time, carrying information about the accelerating masses that created them. When the Sun moves, Earth doesn't feel the change instantly. The gravitational influence travels at light speed, taking about 8 minutes to reach us. We're always orbiting where the Sun was 8 minutes ago, not where it is now. This finite speed of gravity has subtle implications for orbital stability. If gravity propagated instantaneously, orbits would be slightly different. The delay introduces tiny effects that must be accounted for in precise orbital calculations. For the Earth-Sun system, these effects are minuscule, but for systems with stronger gravity and faster orbital speeds, like binary pulsars or merging black holes, they become significant. There's another beautiful aspect of orbital mechanics that's worth contemplating, the three-body problem. When only two bodies interact gravitationally, their orbits can be calculated exactly using relatively simple equations. This is the two-body problem, solved by Newton and refined by subsequent mathematicians. It gives us perfect ellipses, predictable motion, clockwork cosmos. But add a third body, and everything changes. The three-body problem has no general analytical solution. The motion becomes chaotic in the mathematical sense. Tiny changes in initial conditions lead to dramatically different outcomes. This is why we can't predict the exact positions of planets billions of years into the future. The mutual gravitational interactions between all the planets create a complex dance that's ultimately unpredictable in detail, though stable in broad strokes. Earth feels the gravitational pull not just of the Sun, but of every other body in the solar system. Jupiter, despite being hundreds of millions of kilometers away, tugs on Earth with a force that varies as both planets orbit. This force is tiny compared to the Sun's gravity, but over millions of years it causes measurable perturbations in Earth's orbit. Venus, being closer, has a similar effect despite its smaller mass. Even the Moon contributes, its gravity affecting not just Earth's rotation but also its orbit around the Sun. These perturbations don't destabilize Earth's orbit. They're more like gentle nudges that cause our orbital parameters to oscillate slightly around average values. Earth's orbital eccentricity varies between nearly circular and slightly elliptical. The inclination of our orbit relative to the other planets wobbles by tiny amounts. The longitude of perihelion, the direction of Earth's closest approach to the Sun, processes slowly through space. All of these variations are predictable in the short term and bounded in the long term. Computer simulations show that Earth's orbit is stable for at least the next few billion years, until the Sun's evolution begins to significantly change the solar system's dynamics. We're not going to suddenly spiral into the Sun or drift off into interstellar space. Our fall is secure, our orbit robust against perturbations. This stability emerges from the mathematics of orbital dynamics. There's a quantity called the Jacobi integral that remains constant for objects in certain orbital configurations. There are resonances that lock orbital periods into fixed ratios, creating islands of stability in the chaotic sea of possible orbits. There are invariant Taurian phase space, mathematical structures that represent quasi-periodic orbits that persist despite perturbations. The language becomes mathematical, abstract, but the reality it describes is concrete. Earth's orbit is like a groove worn deep into the fabric of space-time, a path that resists deviation. Small perturbations might push us slightly off course, but we're drawn back to the groove, oscillating around the stable solution like a marble rolling in a well-worn track. This is the deeper meaning of our fall around the Sun. It's not a precarious balance that could fail at any moment, but a robust equilibrium that has persisted for billions of years. We're not teetering on the edge of disaster, one perturbation away from catastrophe. We're settled into a comfortable orbit, a sustainable fall that can continue as long as the Sun shines. And this brings us to a profound realization about the nature of stability in the cosmos. Stable orbits aren't the exception, they're the rule. The universe naturally evolves towards stable configurations. Unstable orbits are quickly disrupted, their objects either colliding with other bodies or being ejected from their systems. What remains, what we observe when we look at the night sky, are the survivors, the objects that found stable orbits and kept them. This is a form of cosmic natural selection. Over the billions of years since the solar system formed, countless small bodies have been in unstable orbits. They've collided with planets, fallen into the Sun, or been ejected to interstellar space. The asteroids we see today are the ones in stable orbits. The planets are where they are because those positions are stable. We exist because Earth's orbit has remained in the habitable zone for billions of years. There's something deeply comforting about this cosmic stability. As you lie there in the darkness, you can trust that Earth will continue its orbit tonight, tomorrow, for countless tomorrows to come. The same gravitational embrace that holds you to your bed holds Earth to its path around the Sun. The same physical laws that govern falling apples govern falling planets. There's a unity to it all, a coherence that connects the smallest and largest scales. And yet within this stability, there's still room for wonder, for mystery, for the unexpected. We've discovered exoplanets in configurations we never imagined. Hot Jupiters, orbiting closer to their stars than Mercury orbits our Sun. Planets in binary star systems with figure-8 orbits. Worlds in resonant chains where multiple planets lock into complex rhythmic patterns. Each discovery expands our understanding of what's possible while confirming the underlying physics that governs it all. Some of these exoplanetary systems make our solar system look boring by comparison. There are systems where giant planets migrate inward, destabilizing the orbits of smaller worlds, creating a cosmic game of gravitational billiards. There are systems where planets orbit in opposite directions, or at wild angles to their star's rotation. There are planets that orbit one star in a binary pair, and planets that orbit both stars, tracing complex paths through the competing gravitational fields. Yet even these exotic systems obey the same laws of orbital mechanics that govern Earth's sedate journey around the Sun. They're all falling, all missing their stars in various complex ways. Some falls are simple circles, others are elaborate dances, but the underlying physics is the same. Gravity provides the centripetal force, momentum provides the resistance, and the balance between them creates the orbit. This universality of physical law is one of the most profound discoveries in science. The same equations that describe Earth's orbit around the Sun describe electrons orbiting atomic nuclei, though quantum mechanics adds complications at that scale. The same mathematics appears in fluid dynamics, in population biology, in the oscillations of chemical reactions. There's a deep structure to reality that manifests across scales and contexts, a mathematical poetry that describes the dance of matter and energy through space and time. As you drift deeper into drowsiness, let your mind float with these ideas. You're part of a vast orbital symphony, a cosmic composition where every object plays its part. Earth's orbit is one note in this symphony, sustained for billions of years, harmonizing with the orbits of other planets, contributing to the overall stability and beauty of the solar system. Your own atoms are participating in this orbit, tracing their paths through space as Earth carries them around the Sun. The carbon in your body, forged in the heart of a dying star billions of years ago, has been on countless orbits, around that ancient star, through interstellar space, around the young Sun as part of the primordial disk, and now incorporated into Earth, around our middle-aged star. You're made of well-travelled matter, atoms that know how to fall, how to orbit, how to participate in the cosmic dance. The instruments we've built to observe our cosmic fall are themselves marvels of human ingenuity, each one a testament to our desire to understand our place in the universe. As you settle deeper into rest, imagine these sentinels scattered throughout the solar system, each one listening to the subtle whispers of gravity, light and motion, each one helping us understand the nature of our eternal fall around the Sun. Picture the Parker Solar Probe, humanity's boldest attempt to touch our star. Launched in 2018, this spacecraft is gradually tightening its orbit around the Sun, using Venus's gravity to bend its path inward with each pass. It's falling toward the Sun in a controlled spiral, getting closer than any human-made object has ever been. At its closest approach, it passes within 6 million kilometers of the Sun's surface, 7 times closer than Mercury's orbit. At that distance, the probe experiences sunlight 500 times more intense than what we feel on Earth, temperatures exceeding 400 degrees Celsius, and the full fury of the solar wind. The Parker Solar Probe is teaching us about the very forces that subtly influence planetary orbits. It measures the solar wind directly, sampling the stream of charged particles that flows from the Sun's corona. This wind varies in strength and speed, gusting during solar storms, calming during quiet periods. The probe has discovered that the solar wind doesn't flow smoothly as we once thought, but in complex structures, switchbacks and waves that propagate outward through the solar system. These measurements help us understand one of the subtle forces acting on planetary orbits. the solar wind exerts pressure on everything it touches, a gentle push that, over billions of years, can affect the trajectories of small bodies. For Earth, this pressure is negligible, but knowing its exact strength and variation helps us refine our models of orbital dynamics. Every measurement from Parker Solar Probe adds another decimal place to our understanding of how planets fall around the Sun. The probe itself is in an extreme orbit, one that demonstrates the flexibility of orbital mechanics. Its path is highly elliptical, diving close to the Sun and then swinging back out beyond Venus's orbit. This isn't a stable, eternal orbit like Earth's. The spacecraft needs periodic gravitational assists from Venus to maintain its trajectory, but it shows us that orbits can be sculpted, shaped, modified to serve our purposes. We've learned to use gravity as a tool, to fall in precisely controlled ways. Meanwhile, stationed at a special point in space called the L1 Lagrange point, about 1.5 million kilometers from Earth toward the Sun, floats SOHO, the Solar and Heliospheric Observatory. This spacecraft occupies a gravitational sweet spot where the combined pull of Earth and Sun allows it to orbit the Sun in exactly 1 year despite being closer than Earth. It's like a gravitational eddy, a place where an object can hover relative to the Earth-Sun line. SOHO has been watching the Sun continuously since 1996, never blinking, never looking away. It monitors solar activity, watches coronal mass ejections, tracks sunspots, and measures the solar wind before it reaches Earth. The spacecraft has revolutionized our understanding of our star, but it's also given us something else, a consistent long-term measurement of the Sun's output. You see, one of the questions about planetary orbits is whether they're affected by changes in the Sun itself. Does the Sun's mass change over time? Does its energy output vary in ways that might affect orbital dynamics? SOHO helps answer these questions. It measures the total solar irradiance, the amount of energy the Sun emits, with extraordinary precision. Over its decades of observation, it's shown that the Sun's output varies by only about 0.1% over the 11-year solar cycle, a variation too small to significantly affect planetary orbits. But SOHO has also confirmed that the Sun is slowly losing mass. Through nuclear fusion, the Sun converts about 4 million tons of matter into energy every second. Additionally, the solar wind carries away about 1 million tons of material per second. SOHO's measurements of the solar wind, combined with our understanding of fusion, allow us to calculate that the Sun loses about 10⁻⁴ of its mass each year. This is why planets are very slowly spiraling outward. As the Sun becomes lighter, its gravitational grip weakens. Complementing SOHO are the twin stereo spacecraft, Solar Terrestrial Relations Observatory. Launched in 2006, these two identical spacecraft orbit the Sun, one slightly ahead of Earth and one slightly behind. Together with Earth-based observations, they provide a three-dimensional view of the Sun and its activity. They've watched coronal mass ejections propagate through space, tracked solar storms as they sweep past planets, and helped us understand the three-dimensional structure of the solar wind. The stereo spacecraft are themselves demonstrations of orbital mechanics. Stereo A orbits slightly closer to the Sun than Earth, completing its orbit in less than a year, slowly pulling ahead of Earth. Stereo B was in a slightly larger orbit, falling behind Earth over time. Their separation allowed them to see the far side of the Sun, providing early warning of solar activity that would rotate into view of Earth days later. These solar observatories are complemented by missions to the planets themselves. Messenger, which orbited Mercury from 2011 to 2015, gave us our most precise measurements of the innermost planet's orbit. Mercury is the perfect laboratory for testing our understanding of orbital mechanics, because it experiences the strongest solar gravity and the largest relativistic effects of any planet. Messenger confirmed Einstein's predictions with extraordinary precision. It measured Mercury's orbital precession, that slow rotation of the orbit's orientation that Newton's laws couldn't fully explain. The spacecraft's radio signals, timed with atomic clock precision, showed that Mercury's perihelion, its closest approach to the Sun, advances by 42.98 arc-seconds per century due to general relativity, exactly matching Einstein's calculations from a century ago. But Messenger found more than just confirmation of known physics. It discovered that Mercury's orbit is even more complex than we thought. The planet experiences libration, a slow wobble in its rotation that's coupled to its orbital motion. Mercury rotates exactly 3 times for every 2 orbits around the Sun, a resonance that was captured early in the planet's history and has persisted ever since. This spin-orbit coupling means that certain locations on Mercury experience double sunrises, where the Sun rises, reverses direction, sets, and then rises again. Now Bepi-Colombo, a joint European-Japanese mission, is on its way to Mercury, set to arrive in 2025. This spacecraft is taking a complex path, using gravitational assist from Earth, Venus, and Mercury itself to gradually lower its orbit toward the Sun. It's a 7-year journey to travel to a planet that's never more than 222 million kilometers from Earth. This illustrates a counterintuitive aspect of orbital mechanics. It's often harder to fall toward the Sun than away from it. To reach Mercury, Bepi-Colombo had to lose most of Earth's orbital velocity. If you simply pointed a rocket at Mercury and fired, you'd need enormous amounts of fuel to cancel Earth's sideways motion. Instead, the spacecraft uses planetary flybys to gradually shed velocity, letting gravity do the work that rockets would otherwise have to do. Each flyby bends the spacecraft's trajectory, adjusting its fall around the Sun until it matches Mercury's orbit. When Bepi-Colombo arrives, it will split into 2 separate orbiters, each studying different aspects of Mercury and its environment. They'll measure the planet's gravity field with unprecedented precision, map its surface composition, study its magnetic field, and monitor its interaction with the solar wind. Every measurement will add to our understanding of how planets behave in the intense gravitational and radiation environment close to the Sun. Moving outward from the Sun, we find Cassini's legacy at Saturn. Though the mission ended in 2017 with a deliberate plunge into Saturn's atmosphere, its 13 years of observations revolutionized our understanding of orbital dynamics in complex systems. Saturn, with its dozens of moons and spectacular rings, is like a miniature solar system, a laboratory for studying gravitational interactions. Cassini watched shepherd moons carve gaps in Saturn's rings, their gravity creating intricate patterns in the orbiting ice particles. It observed how the moon Enceladus feeds Saturn's E-ring with geysers from its subsurface ocean. It tracked the orbital resonances between moons that keep their orbits stable over billions of years. Every observation was a lesson in how gravity shapes the motion of objects large and small. One of Cassini's most beautiful discoveries was the propeller-shaped gaps created by tiny moonlets embedded in Saturn's rings. These moonlets, some only a few hundred meters across, clear small gaps in the ring material as they orbit. But the gaps aren't simple. Coriolis forces and the differential rotation of the rings create elaborate patterns that look like propeller blades when viewed from above. It's orbital mechanics made visible, the same forces that govern Earth's fall around the Sun played out in miniature in Saturn's rings. Cassini also made precise measurements of Saturn's gravitational field by carefully tracking how the planet's gravity affected the spacecraft's orbit. These measurements revealed that Saturn's core is larger and more diffuse than expected, and that the planet's famous winds extend deep into its interior. The spacecraft even detected tiny variations in Saturn's gravity, caused by the gravitational pull of the rings themselves, a mass equivalent to about 40% of Saturn's moon Mimas, spread out in a disk thousands of kilometers wide but only tens of meters thick. Now Juno continues this work at Jupiter, orbiting the giant planet since 2016. Juno follows a highly elliptical polar orbit, diving close to Jupiter's cloud tops and then swinging far out to avoid the planet's intense radiation belts. Each orbit is a controlled fall, a careful balance between getting close enough to make detailed measurements and staying far enough away to survive. Juno has revealed that Jupiter's interior is far more complex than we imagined. The planet's Great Red Spot extends hundreds of kilometers into the atmosphere. Its magnetic field is lumpy and irregular, unlike the relatively smooth fields of Earth or Saturn. Its core appears to be partially dissolved, dilute, spread out rather than concentrated in a compact ball. All of these discoveries affect our understanding of how Jupiter influences the orbits of other bodies in the solar system. Jupiter, being the most massive planet, acts as the solar system's gravitational shepherd. Its immense gravity influences the orbits of asteroids, comets, and even the other planets. Juno's precise measurements of Jupiter's gravity field help us understand exactly how this influence works. The spacecraft has detected gravitational anomalies that reveal deep atmospheric flows, measured the gravitational signature of Jupiter's moons as they tug on the spacecraft, and tracked how Jupiter's rapid rotation distorts its gravitational field. Far beyond the giant planets, New Horizons continues its journey into the Kuiper Belt after its historic flyby of Pluto in 2015. This spacecraft is climbing out of the Sun's gravitational well, falling upward in a sense, using the momentum from its launch and a gravitational assist from Jupiter to escape the Sun's pull. It's showing us what happens when an object has enough energy to break free from closed orbits and trace an open path to infinity. New Horizons' trajectory is a hyperbola, an open curve that will never return to the Sun. It's still falling in the Sun's gravitational field, still being pulled back, but it's moving fast enough that the pull will never stop it, only slow it down. As it travels farther from the Sun, it gradually decelerates, trading kinetic energy for gravitational potential energy. But it will never stop, never fall back, never complete an orbit. The spacecraft's measurements of the Kuiper Belt objects it encounters help us understand the outer reaches of the solar system, where the Sun's gravity becomes weak and orbital periods stretch to centuries. Out here, orbits are easily perturbed by passing stars, by the gravitational tide of the galaxy itself. New Horizons is exploring the boundary between the Sun's gravitational domain and the wider cosmos. But perhaps the most ambitious orbital observatory is Gaia, a European Space Agency mission that's creating a three-dimensional map of our galaxy. Stationed at the L2 Lagrange point, 1.5 million kilometers from Earth in the opposite direction from the Sun, Gaia slowly rotates, scanning the entire sky every 6 months. It measures the positions and motions of stars with unprecedented precision, tracking how they move through space over the years of its mission. Gaia's measurements are so precise that it must account for the subtle effects of relativity on light from distant stars. As Earth orbits the Sun, our changing velocity causes tiny Doppler shifts in starlight. Our acceleration toward the Sun causes an even tinier effect called aberration, where stars appear to shift position slightly. Gaia measures these effects and uses them to refine our understanding of Earth's orbit to extraordinary precision. The spacecraft has measured the positions of over 1.8 billion stars, tracking their motion through space. This allows astronomers to calculate the gravitational field of our galaxy and understand how the Sun's orbit around the galactic center is influenced by the combined pull of hundreds of billions of stars. We're discovering that the Sun's galactic orbit is more complex than we thought, influenced by spiral arms, giant molecular clouds, and the galaxy's dark matter halo. Gaia has also discovered thousands of asteroids in our own solar system, tracking their orbits with precision that allows us to predict their positions centuries into the future. Some of these asteroids have orbits that bring them close to Earth, and Gaia's measurements help us assess the risk of future impacts. The spacecraft has even detected the tiny wobbles in stars' positions caused by orbiting planets, contributing to our census of exoplanets. All of these spacecraft, these robotic explorers scattered throughout the solar system and beyond, are connected by invisible threads of radio waves to giant dish antennas on Earth. The Deep Space Network, with facilities in California, Spain, and Australia, maintains constant contact with our distant emissaries. Every command sent, every bit of data received, must account for the orbital motion of Earth and the spacecraft. When mission controllers send a command to a spacecraft, they must aim not at where the spacecraft is now, but where it will be when the radio signal arrives. For New Horizons, currently about 8 billion kilometers from Earth, this means predicting the spacecraft's position 7.5 hours in the future. The calculations must account for Earth's rotation, Earth's orbital motion around the Sun, the spacecraft's trajectory, and even the tiny delays caused by the Sun's gravity bending the path of radio waves. The precision required is staggering. To communicate with Voyager 1, now over 24 billion kilometers away, antennas must point with an accuracy of a few thousandths of a degree. That's like hitting a dime with a laser pointer from 10 kilometers away, and the pointing must continuously adjust to account for Earth's rotation and orbital motion. We're literally chasing our spacecraft across the sky as Earth carries us around the Sun. These communications themselves provide valuable scientific data. By precisely timing radio signals, we can measure the distance to spacecraft with meter-level accuracy across billions of kilometers. Doppler shifts in the signals tell us the spacecraft's velocity to within millimeters per second. These measurements are so sensitive that they've detected the gravitational pull of individual mountains on asteroids, the atmospheric drag on Mars orbiters, and even the tiny thrust from sunlight hitting spacecraft solar panels. The most dramatic example of using radio signals for science was the Cassini mission's grand finale. As the spacecraft made its final orbits between Saturn and its rings, scientists carefully tracked how Saturn's gravity affected the spacecraft's velocity. The Doppler shift in Cassini's radio signal, measured to a precision of 0.01 millimeters per second, allowed scientists to weigh the rings and determine their age. They found that the rings contain about 15 million billion tons of ice and rock and are probably only 100 million years old, young compared to Saturn itself. Another beautiful example comes from the Juno mission. As the spacecraft orbits Jupiter, the planet's gravity accelerates and decelerates it in a predictable pattern. But there are tiny deviations from the expected pattern, caused by irregularities in Jupiter's gravitational field. By measuring these deviations through their effect on Juno's radio signals, scientists can peer inside Jupiter, mapping the distribution of mass in its interior. It's like giving the planet an MRI scan using nothing but the Doppler shift of radio waves. Even more remarkably, we can use these techniques to test fundamental physics. The Cassini spacecraft conducted several tests of general relativity during its mission. As its radio signals passed near the Sun on their way to Earth, they were delayed by the warping of spacetime near our star. This Shapiro delay, named after the physicist who predicted it, amounted to about 200 microseconds for signals grazing the Sun's surface. Cassini measured this delay to a precision of 0.2%, confirming Einstein's predictions. These spacecraft also experienced something called the Pioneer anomaly, named after the Pioneer 10 and 11 spacecraft that first exhibited it. As these spacecraft traveled to the outer solar system, they experienced a tiny unexpected acceleration toward the Sun, about 10 billion times weaker than Earth's surface gravity. For years, this anomaly puzzled scientists. Was it a sign of new physics? A modification to gravity at very weak accelerations? The answer turned out to be beautifully mundane: thermal radiation. The Pioneer spacecraft were powered by radioisotope thermoelectric generators that produced heat. This heat radiated into space, but not uniformly. More heat radiated from the back of the spacecraft than the front, creating a tiny thrust that slowed them down. It was the Yarkovsky effect in action, the same phenomenon that affects asteroids, but now measured precisely in our own spacecraft. This discovery highlighted just how sensitive our measurements have become. We can detect forces so weak that the pressure from the heat radiated by a warm spacecraft becomes significant. Every photon carries momentum, and when enough photons are emitted preferentially in one direction, they create thrust. This photon pressure is now deliberately used in some missions. Solar sails use the pressure of sunlight itself for propulsion, falling around the Sun while being pushed by its light. The Japanese spacecraft Icaros demonstrated this technology, deploying a 14-meter-wide solar sail in 2010. The pressure from sunlight on this sail is incredibly weak, about 1.12 millinewtons, the weight of a grain of salt. But in the frictionless environment of space, this tiny force continuously accelerates the spacecraft. Icaros successfully flew by Venus, proving that we can sail on sunlight, riding the very photons that warm our planet. LightSail 2, a crowd-funded mission by the Planetary Society, has been demonstrating controlled solar sailing in Earth orbit since 2019. The spacecraft, about the size of a loaf of bread, deployed a sail the size of a boxing ring. By adjusting the sail's orientation relative to the Sun, mission controllers can raise or lower the spacecraft's orbit. It's sailing in space using light pressure to modify its fall around Earth. These solar sail missions are preparing for even more ambitious projects. Breakthrough Starshot proposes using powerful lasers to push tiny spacecraft with light sails to 20% of the speed of light, fast enough to reach the nearest star in 20 years. At such speeds, the spacecraft would no longer be orbiting the Sun. They would be on hyperbolic trajectories, escaping not just the solar system but traveling fast enough to cross interstellar distances in a human lifetime. But even our current spacecraft, traveling at more modest speeds, are teaching us about the boundaries of the Sun's gravitational influence. The Voyager spacecraft, launched in 1977, have now entered interstellar space, beyond the heliopause where the solar wind meets the interstellar medium. Yet they're still within the Sun's gravitational sphere of influence, still technically orbiting our star, though so weakly that passing stars and the galactic tide significantly affect their trajectories. Voyager 1 is currently about 24 billion kilometers from the Sun, traveling at about 17 kilometers per second. At this distance, the Sun's gravity is 40,000 times weaker than at Earth's orbit, but it's still there, still pulling, still trying to curve Voyager's path into a closed orbit. But Voyager is moving too fast, has too much energy. It will continue falling away from the Sun forever, its hyperbolic trajectory gradually straightening as the Sun's influence weakens. The Voyagers carry golden records, messages from Earth to any civilization that might find them in the distant future. These records include sounds and images from Earth, greetings in multiple languages, and music from different cultures. But they also include something else, precise diagrams showing Earth's location relative to 14 pulsars. These pulsars act as cosmic lighthouses, their regular pulses providing a galactic positioning system. Any civilization that finds Voyager could use these pulsar maps to determine exactly where and when the spacecraft came from. This assumes, of course, that the pulsars will still be recognizable in the far future. Pulsars gradually slow down, their pulses becoming less frequent over millions of years. The maps on the golden record include the pulse periods of the pulsars at the time of launch, allowing a future civilization to calculate how much time has passed. It's a timestamp written in the rotation of dead stars, a way of marking our moment in cosmic history. As the Voyagers continue their journey, they're also conducting the longest duration experiment in human history. Their radioisotope thermoelectric generators gradually decay, producing less power each year. Their instruments shut down one by one as power becomes insufficient. By 2025, we expect to lose contact with them entirely as their transmitters fall silent, but they'll continue their journey in silence, falling through interstellar space for millions of years. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. Voyager 2 will pass within 1.7 light-years of Ross 248 in about the same time frame. These encounters won't be close enough to significantly alter the spacecraft's trajectories. They'll continue wandering through the galaxy, occasionally passing near stars, occasionally feeling their gravitational pull, but never being captured into orbit. The Voyagers are now participating in a different kind of fall, the fall of the entire solar system through the galaxy. The Sun and all its planets orbit the center of the Milky Way at about 220 kilometers per second, completing one galactic year every 230 million Earth years. We've completed about 20 galactic orbits since the solar system formed. The dinosaurs lived 1 galactic year ago. The entire history of complex life on Earth spans just 2 galactic years. As we orbit the galaxy, we oscillate up and down through the galactic disk, like horses on a carousel. This oscillation has a period of about 70 million years. Some scientists have suggested that these passages through the denser parts of the galactic disk might trigger comet showers from the Oort cloud, potentially causing mass extinctions on Earth. It's a controversial idea, but it illustrates how our fall around the Sun is nested within larger falls on galactic scales. We're also falling with the entire galaxy as it moves through space. The Milky Way and Andromeda galaxies are falling toward each other at about 110 kilometers per second, destined to collide in about 4.5 billion years. This collision won't be the catastrophe it might sound like. Galaxies are mostly empty space, and the chance of stars actually colliding is vanishingly small. But the gravitational interactions will dramatically reshape both galaxies, potentially ejecting the solar system into intergalactic space, or sending it plunging toward the merged galactic center. Even this galactic collision is part of a larger pattern. Our local group of galaxies is falling toward the Virgo cluster at about 600 kilometers per second. The Virgo cluster and our local group are both falling toward the Great Attractor, a gravitational anomaly hundreds of millions of light-years away. And everything in our cosmic neighborhood is falling toward the Shapley supercluster, one of the largest known structures in the universe. These cosmic flows reveal that falling never really ends. There's no fixed reference frame, no absolute rest. Everything is falling relative to something else. Earth falls around the Sun falls around the galaxy falls toward Andromeda, and all of it falls through the expanding universe. We're nested falls within falls, circles within circles, a cosmic mandala of motion that extends from the smallest scales to the largest. Our instruments have revealed this hierarchy of motion with ever-increasing precision. The Planck satellite mapped the cosmic microwave background, the afterglow of the Big Bang, with such accuracy that it could detect our motion through the universe. The entire solar system is moving at about 370 kilometers per second relative to this cosmic backdrop, heading toward the constellation Leo. This motion creates a tiny Doppler shift in the cosmic microwave background. It appears slightly warmer in the direction we're moving, slightly cooler behind us. Even gravitational wave detectors, the most sensitive instruments ever built, must account for Earth's orbital motion. When LIGO and Virgo detect gravitational waves from colliding black holes billions of light years away, the signals arrive at slightly different times at different detectors due to Earth's motion. The time delays tell us the direction to the source, but calculating them requires precise knowledge of Earth's position and velocity in its orbit around the Sun. These detectors can measure changes in distance smaller than a proton's width, sensing the stretching and squeezing of space itself as gravitational waves pass through Earth. They've detected dozens of black hole collisions, each one a cosmic catastrophe that sends ripples through the fabric of space-time. These ripples travel at the speed of the light, washing over Earth and every other orbiting body, momentarily distorting their paths by an infinitesimal amount. The future promises even more sensitive instruments. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will be a gravitational wave detector in space. 3 spacecraft will orbit the Sun in a triangular formation, each separated by 2.5 million kilometers. Laser beams between the spacecraft will measure their separation to picometer precision, detecting gravitational waves at much lower frequencies than ground-based detectors can observe. LISA will be sensitive enough to detect the gravitational waves from binary star systems in our own galaxy. It will hear the gravitational hum of thousands of white dwarf binaries, the spiraling death dances of stellar remnants. It might even detect the gravitational waves from the early universe, echoes of cosmic inflation that occurred in the first fraction of a second after the Big Bang. These primordial gravitational waves would tell us about the universe when it was younger than a heartbeat, when the forces that govern falling and orbiting were just beginning to take their current forms. As you lie there in the darkness, perhaps you can imagine these instruments scattered throughout the solar system and beyond, each one listening to the cosmos in its own way. Parker Solar Probe diving toward the Sun, feeling the solar wind's breath. Soho and Stereo watching our star's every movement. Bepi Colombo falling toward Mercury, preparing to study the innermost planet's complex dance. Juno circling Jupiter, measuring the giant planet's deep currents. New Horizons climbing toward the stars, still calling home across billions of kilometers. They're all falling, just like Earth, just like you. They're following paths through space-time, paths we've calculated and planned and adjusted with extraordinary precision. We've become masters of orbital mechanics, able to send our robotic avatars on complex journeys that would have seemed like magic to our ancestors. We can make them fall in just the right way to visit other worlds, to sample the solar wind, to touch the sun itself. And through their electronic eyes, we see our own fall more clearly. We understand that Earth's orbit isn't just a circle in space, but a spiral through time, carrying us into the future at 1 second per second, 1 year per orbit. We see that our fall around the sun is part of a vast hierarchy of motion that connects us to the entire universe. We're not separate from the cosmos, watching it from outside. We're embedded in it, woven into its fabric, falling through it in beautiful, complex patterns. The data from these missions flows back to Earth continuously, a stream of numbers that encode the secrets of orbital motion. Scientists around the world analyze these numbers, looking for patterns, testing theories, discovering surprises. Each measurement adds to our understanding, each observation refines our models. We're building a picture of the solar system's dynamics with ever-increasing resolution, like a photograph that becomes sharper with each passing year. And what we're finding is both reassuring and wondrous. Earth's orbit is stable, our fall around the sun secure for billions of years to come. But within that stability is incredible complexity, resonances and perturbations, cycles within cycles, subtle forces that paint elaborate patterns in the paths of planets. The solar system isn't a simple clockwork, but a rich dynamical system, deterministic yet capable of surprise, predictable in broad strokes yet full of fine details we're still discovering. Now we come to one of the most beautiful paradoxes in our story of planetary motion. While everything we've discussed suggests that planets should slowly spiral inward as they lose energy to various processes, The reality is quite the opposite. Earth, along with all the other planets, is actually drifting away from the Sun, moving outward by tiny amounts each year. This isn't a failure of our understanding, but rather a beautiful confirmation of it, revealing how multiple effects combine to create the actual evolution of planetary orbits. The key to this paradox lies in the Sun itself. Our star, that massive ball of fusing hydrogen that holds the entire solar system in its gravitational embrace, is slowly losing mass. This mass loss happens through two primary mechanisms, both fundamental to what makes the Sun shine. First, there's the conversion of matter into energy through nuclear fusion. Deep in the Sun's core, where temperatures reach 15 million degrees Celsius and pressures are 250 billion times Earth's atmospheric pressure, hydrogen nuclei are forced together to create helium. This fusion process is beautifully elegant. 4 hydrogen nuclei, each just a single proton, combine through a series of reactions to create one helium nucleus containing 2 protons and 2 neutrons. But here's the remarkable thing. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that created it. The difference, about 0.7% of the original mass, is converted directly into energy according to Einstein's famous equation E=mc2. This is the source of sunlight, the energy that warms Earth and powers nearly all life on our planet. The numbers involved are staggering. Every second, the Sun converts about 620 million tons of hydrogen into 616 billion tons of helium. The missing 4 million tons becomes pure energy, light, heat, and other forms of radiation that stream out into space. That's 4 million tons of matter annihilated every second, transformed from substance into radiance. In the time it takes you to read this sentence, the Sun has converted more mass into energy than all the matter in Mount Everest. This energy takes a remarkably long time to escape the Sun. Generated in the core, photons of light begin a random walk toward the surface, absorbed and re-emitted countless times by the dense solar material. A photon might travel only a few millimeters before being absorbed, then re-emitted in a random direction. This process repeats billions upon billions of times. On average, it takes between 10,000 and 170,000 years for energy to travel from the Sun's core to its surface, a journey that would take light just 2.3 seconds if it could travel in a straight line. Once the energy reaches the Sun's surface, the photosphere, it streams into space at the speed of light. 8 minutes later, a tiny fraction of it reaches Earth, delivering about 1,361 watts per square meter at the top of our atmosphere. This solar constant, as it's called, has been remarkably stable throughout Earth's history, varying by less than 0.1% over the solar cycle and increasing very gradually as the Sun ages. But the Sun loses mass through another mechanism as well, the solar wind. This stream of charged particles, mostly protons and electrons, flows continuously from the Sun's corona, its outer atmosphere. The corona is paradoxically much hotter than the Sun's surface, reaching temperatures of millions of degrees. At these temperatures, particles have enough energy to escape the Sun's gravity, streaming outward at speeds ranging from 300 to 800 kilometers per second. The solar wind carries away about 1 million tons of the Sun's mass every second. While this is less than the mass lost through fusion, it's still significant. Combined with the fusion mass loss, the Sun loses about 5 million tons per second, or about 150 trillion tons per year. Over the Sun's lifetime so far, it has lost about 0.03% of its original mass, equivalent to about 100 Earth masses. This might seem like a lot, but remember that the Sun is incredibly massive. It contains 99.86% of all the mass in the solar system, about 333,000 times Earth's mass. The Sun could lose an Earth's worth of mass, and it would represent only 0.03% of its total. Even after billions of years of fusion and solar wind, the Sun has lost only a tiny fraction of its original mass. But even this tiny fraction has profound effects on planetary orbits. As the Sun loses mass, its gravitational pull weakens. This is a direct consequence of Newton's law of gravitation. The force between two objects is proportional to the product of their masses. If one mass decreases, so does the force. For planets orbiting the Sun, this weakening gravity means they need less centripetal force to maintain their orbits. The result is that they gradually drift outward, their orbits expanding to maintain the balance between gravity and their orbital motion. The mathematics of this are elegant. The orbital radius of a planet is inversely proportional to the Sun's mass for a given orbital angular momentum. As the Sun's mass decreases, the orbital radius must increase to conserve. Angular momentum is like a figure skater extending their arms to slow their spin, except in reverse. The planets move outward as the Sun becomes lighter, maintaining their angular momentum while adjusting to the weaker gravitational field. The rate of this outward drift is tiny but calculable. Earth moves away from the Sun by about 1.5 centimeters per year due to solar mass loss. That's about the rate at which your fingernails grow. In the 4.5 billion years since Earth formed, our planet has drifted outward by perhaps 60,000 kilometers due to this effect. While this sounds like a large distance, it's only 0.04% of Earth's current orbital radius. We're 0.04% farther from the Sun than we were when Earth was young. This outward drift will continue as long as the Sun shines. Over the next billion years, Earth will move outward by another 15,000 kilometers or so. In 5 billion years, when the Sun exhausts its hydrogen fuel and begins to die, Earth will be about 75,000 kilometers farther from the Sun than it is today, assuming it survives that long. The gradual outward drift provides a tiny bit of compensation for the Sun's gradually increasing brightness, though not nearly enough to prevent Earth from eventually becoming too hot for life. The Sun's mass loss affects all the planets, but the effect is most pronounced for the outer planets. This is because the fractional change in orbital radius is the same for all planets, but the absolute change is larger for planets that are already far from the Sun. Neptune, for instance, drifts outward by about 45 centimeters per year, 30 times more than Earth in absolute terms, though the same in percentage terms. This uniform percentage expansion means the architecture of the solar system is preserved even as it slowly expands. The ratios between planetary orbits remain constant. If Earth is 1 astronomical unit from the Sun, and Mars is 1.5 astronomical units, that 1.5.1 ratio is maintained even as both orbits expand. The solar system is like a photograph being slowly enlarged, maintaining its proportions while growing in scale. But the Sun's mass loss isn't perfectly steady. It varies with the solar cycle, the roughly 11-year period over which the Sun's activity waxes and wanes. During solar maximum, when sunspots are common and solar storms frequent, the solar wind is stronger and more mass is lost. During solar minimum, the wind weakens and mass loss decreases. These variations are tiny, perhaps a 20% change in the solar wind mass loss rate, but they create subtle oscillations in the rate at which planets drift outward. There are also dramatic events called coronal mass ejections, where the Sun explosively ejects billions of tons of material in a matter of hours. These events can temporarily increase the Sun's mass loss rate by orders of magnitude. A large coronal mass ejection might eject 10 billion tons of material, as much as the Sun normally loses in 2 hours. While impressive, these events are too rare and too small to significantly affect planetary orbits. Earth would need to be hit by millions of such ejections to measurably change its orbit. The Sun's mass loss will accelerate dramatically in the distant future. In about 5 billion years, when the Sun exhausts the hydrogen in its core, it will begin fusing helium. This will cause it to expand into a red giant, potentially engulfing Mercury and Venus. During this phase, the Sun will lose mass much more rapidly through an enhanced stellar wind. Models suggest the Sun might lose 25–30% of its mass during its red giant phase, causing the surviving planets to migrate outward significantly. This future mass loss might actually save Earth from being engulfed by the expanding Sun. As the Sun loses mass and Earth spirals outward, it might just barely escape being swallowed. Current models suggest it's a close call. Earth's fate depends on exactly how much mass the Sun loses and how quickly it loses it. Mars, being farther out, will definitely survive, moving outward to perhaps 1.7 times its current distance from the Sun. But let's return to the present, to the gentle, steady mass loss happening right now. This mass loss has been confirmed through multiple independent measurements. We can measure the Sun's mass loss indirectly by observing its effects on planetary orbits. The most precise measurements come from tracking spacecraft, whose trajectories are affected by the Sun's changing gravity. The Messenger spacecraft, during its journey to Mercury, provided some of the best data. By precisely tracking the spacecraft's radio signals, scientists could measure tiny changes in its trajectory caused by the Sun's gravity. Over the course of the mission, They detected the subtle weakening of solar gravity due to mass loss. The measured rate matched theoretical predictions based on our understanding of fusion and the solar wind. Even more precise measurements may come from future missions. The proposed Sunrise mission would use radio interferometry to map the Sun's gravitational field with unprecedented accuracy. By tracking how the Sun's gravity bends radio waves from distant quasars, the mission could measure solar mass loss to a precision of parts per trillion per year. This would allow us to separate the contributions from fusion and the solar wind, testing our understanding of both processes. The solar wind itself is a fascinating phenomenon that deserves deeper exploration. It's not a uniform flow, but has a complex structure that reflects the Sun's magnetic field. Near the Sun's equator, the wind is slow, about 400 kilometers per second, and dense. At higher latitudes it's fast, up to 800 kilometers per second, but less dense. This creates a pattern like a spiral garden sprinkler, with alternating streams of fast and slow wind rotating with the Sun. Earth passes through these different wind streams as they rotate past us, experiencing changes in solar wind pressure and density. When a fast stream overtakes a slow stream, it creates a compression region that can trigger geomagnetic storms when it hits Earth. These storms can create spectacular auroras, disrupt satellite communications, and even induce currents in power grids. But they don't significantly affect Earth's orbit. The total momentum transfer is far too small. The solar wind extends far beyond the planets, creating a vast bubble in space called the heliosphere. This bubble extends about 120 astronomical units from the Sun, nearly 3 times Neptune's orbital distance. Beyond this boundary, called the heliopause, lies interstellar space, where the solar wind finally succumbs to the pressure of the interstellar medium. The Voyager spacecraft have crossed this boundary, becoming humanity's first interstellar travelers. But even beyond the heliopause, the Sun's gravity continues to dominate. The gravitational sphere of influence of the Sun, the region where its gravity is stronger than the combined pull of nearby stars, extends much farther, perhaps 100,000 astronomical units or more. This is the realm of the Oort cloud, a vast spherical shell of icy bodies that occasionally fall inward to become long-period comets. These objects are still orbiting the Sun, still falling around it, even though they're so far away that the solar wind has no effect on them. The Oort cloud objects are affected by solar mass loss too, but in a different way than the planets. Being so far from the Sun, they feel its gravity only weakly. A small change in the Sun's mass can significantly affect their orbits. As the Sun loses mass, Oort cloud objects drift outward, and some that were barely bound to the solar system might escape entirely, drifting off into interstellar space. This raises an interesting question. How many objects has the solar system lost over its history due to solar mass loss? The answer is probably very few. While the Sun has lost about 100 Earth masses over its lifetime, this represents only 0.03% of its original mass. Objects would need to be right on the edge of being gravitationally bound for such a small change to allow them to escape. Most objects that were going to escape probably did so long ago, ejected by gravitational interactions with the planets rather than by solar mass loss. The interplay between solar mass loss and orbital dynamics reveals something profound about the solar system. It's not a static structure, but an evolving one. The orbits we see today are not exactly the same as they were billions of years ago or will be billions of years in the future. The solar system is slowly expanding, aging, changing in subtle ways that are almost imperceptible on human timescales but significant over cosmic time. This evolution is remarkably gentle. Unlike many stellar systems where planets migrate dramatically or are ejected entirely, our solar system has remained stable for billions of years. The slow outward drift due to solar mass loss is the dominant long-term change, and it's so gradual that life has had plenty of time to evolve and adapt. If Earth's orbit were changing rapidly, if our distance from the Sun varied significantly over millions of years, complex life might never have had the chance to develop. The stability of this slow expansion is maintained by the conservation laws of physics. Angular momentum is conserved as planets drift outward, maintaining the relationship between orbital radius and velocity. Energy is conserved too, with the gravitational potential energy lost as the Sun's mass decreases, balanced by changes in orbital kinetic energy. These conservation laws act like guardrails, preventing dramatic changes and ensuring smooth, predictable evolution. There's something poetic about this outward drift. As the sun ages and slowly fades, it releases its gravitational grip on its planets, allowing them to drift away like children leaving home. The process is so slow that it's almost tender, a gradual loosening rather than a sudden release. By the time the sun dies, the planets will be significantly farther away, as if maintaining a respectful distance from their dying parent star. This process is happening throughout the universe. Every star that shines is losing mass, and every planet orbiting those stars is slowly drifting outward. It's a universal phenomenon, as fundamental to planetary systems as orbits themselves. When we observe exoplanets around other stars, we're seeing them at particular moments in their outward journeys, snapshots of a process that continues throughout their stars' lifetimes. The implications of our cosmic fall extend far beyond abstract physics and distant spacecraft. Here on Earth, as you lie in the comfort of your bed, you're intimately connected to this grand orbital dance in ways that shape every aspect of your existence. The rhythm of your days, the cycle of your seasons, even the beating of your heart are all tuned to Earth's perpetual fall around the sun. We are not merely observers of this cosmic motion, we are participants. Our bodies and minds evolved to harmonize with the orbital rhythms that have remained constant for billions of years. Consider the miracle of the 24-hour day. This period, which seems so natural to us that we rarely question it, is actually the result of a complex interplay between Earth's rotation and its orbit around the sun. A sidereal day, the time it takes Earth to rotate once relative to the stars, is about 23 hours and 56 minutes. But because Earth is also orbiting the sun, moving about 1 degree along its orbit each day, it must rotate a little extra for the sun to return to the same position in the sky. Those extra 4 minutes give us our 24-hour solar day, the rhythm that governs all life on Earth. This daily cycle is encoded in nearly every cell of your body, deep within your brain, in a tiny region called the suprachiasmatic nucleus. About 20,000 neurons act as your master clock. These cells generate a rhythm that's remarkably close to 24 hours, even in complete darkness, a biological echo of Earth's rotation. This circadian rhythm influences everything from your body temperature to your hormone levels, from your alertness to your metabolism. You are, in a very real sense, a living embodiment of Earth's spin. But Earth's rotation is gradually slowing due to tidal friction, primarily from the Moon, but also to a lesser extent from the Sun. 4 billion years ago, a day lasted only about 6 hours. When the first life forms emerged, they experienced a world spinning 4 times faster than today. As Earth's rotation slowed over geological time, life adapted, gradually adjusting its biological rhythms to match the lengthening day. The 24-hour circadian rhythm that seems so fundamental to our biology is actually a recent development in Earth's history. Currently, Earth's rotation is slowing by about 1.7 milliseconds per century. This might seem insignificant, but it adds up over time. Since the emergence of human civilization about 10,000 years ago, the day has lengthened by about 0.17 seconds. Ancient astronomical observations confirm this. Eclipses recorded thousands of years ago occurred at slightly different times than they would have if Earth's rotation had remained constant. We can actually measure the changing length of the day by comparing ancient eclipse records with modern calculations. This slowing rotation has profound implications for our future. In about 180 million years, a day will last 25 hours. Life will need to adapt its circadian rhythms once again. In the very distant future, perhaps 50 billion years from now if Earth still existed, our planet would become tidally locked to the Moon, with the same face always pointing toward our celestial companion. A day would last as long as a lunar month, currently about 29.5 days, but much longer by then, as the Moon continues to drift away. The leap second, added occasionally to our clocks to keep them synchronized with Earth's rotation, is a modern acknowledgement of this ongoing change. Since 1972, we've added 27 leap seconds to coordinated universal time. Each one represents a moment when human timekeeping must bend to accommodate the reality of our changing cosmic motion. We're constantly adjusting our artificial constructs of time to match the actual movement of our planet. But it's not just the daily cycle that connects us to our orbital motion. The annual journey around the sun creates the seasons that have shaped the evolution of life and the development of human civilization. The 23.5 degree tilt of Earth's axis, stabilized by the Moon's gravitational influence, ensures that different parts of Earth receive varying amounts of sunlight throughout the year. This variation drives weather patterns, ocean currents, and the great migrations and life cycles of countless species. Your own body responds to these seasonal changes in subtle ways. Melatonin production increases during winter's longer nights. Vitamin D synthesis decreases with reduced sunlight exposure. Some people experience seasonal affective disorder, their mood and energy levels fluctuating with the changing angle of sunlight. We are solar-powered beings, our biochemistry attuned to our planet's orbital position. The history of human civilization is inseparable from our awareness of Earth's orbital cycles. Agriculture, the foundation of settled civilization, depends entirely on understanding and predicting the seasons. Ancient farmers needed to know when to plant and when to harvest, knowledge that required careful observation of the sun's position in the sky. The first calendars were attempts to reconcile the daily, monthly, and annual cycles, the rotation of Earth, the orbit of the Moon, and the orbit of Earth around the Sun. This reconciliation has never been perfect because these cycles don't align neatly. A year is not exactly 365 days, but about 365.42 Manas days. This extra quarter day is why we need leap years, adding February 29th every 4 years. But even that's not quite right. The 0.24+219 isn't exactly 0.25, so we skip leap years in years divisible by 100, unless they're also divisible by 400. These rules, seemingly arbitrary, are actually precise adjustments to keep our calendar aligned with Earth's orbit. Different cultures have developed different solutions to this orbital arithmetic. The Islamic calendar ignores the solar year entirely, following only lunar months, which is why Ramadan drifts through the seasons. The Hebrew calendar adds entire leap months to keep lunar and solar cycles roughly aligned. The ancient Maya developed incredibly sophisticated calendars that tracked multiple cycles simultaneously, including the synodic period of Venus and the orbital period of Mars. Our modern Gregorian calendar, introduced in 1582, is accurate to about 1 day in 3,236 years. But even this impressive precision isn't perfect. Proposals for calendar reform continue to appear, seeking to better align human timekeeping with cosmic motion. Each proposal represents another attempt to reconcile our artificial constructs with the natural rhythms of our fall around the Sun. The economic implications of our orbital motion are enormous. Seasonal industries, agriculture, tourism, energy, all depend on predictable orbital cycles. The growing season, determined by Earth's position in its orbit, dictates when crops can be planted and harvested. Winter heating and summer cooling demands fluctuate with our orbital position. Holiday shopping seasons tied to solstices and equinoxes through ancient traditions drive retail economies. We've built our entire economic system around the assumption that Earth's orbit will remain stable and predictable. Even the stock market shows orbital influences. The January effect was Lauhe, where stocks tend to rise in January, may be partly psychological, but is tied to the calendar year that itself is defined by Earth's orbit. Commodity prices for agricultural products fluctuate seasonally. Energy futures reflect anticipated heating and cooling demands. Our financial systems are deeply intertwined with our cosmic motion, though most traders probably don't think of themselves as betting on orbital mechanics. Climate and weather, those powerful forces that shape human history, are fundamentally driven by our orbit around the Sun. The distribution of solar energy across Earth's surface, varying with latitude and season, drives atmospheric circulation. The temperature difference between equator and poles, created by Earth's spherical shape and axial tilt, generates the jet streams and trade winds. Ocean currents, like the Gulf Stream that keeps Europe warm, are ultimately powered by orbital dynamics. The Milankovitch cycles, those subtle variations in Earth's orbit and rotation that drive ice ages, have profoundly influenced human evolution. The last ice age, which ended about 11,700 years ago, forced our ancestors to adapt, migrate, and innovate. The pressure of changing climate may have driven the development of agriculture, as traditional food sources became scarce. The current interglacial period, a warm phase between ice ages, has provided the stable climate that allowed civilization to flourish. We're currently in a particularly stable phase of these orbital cycles. Earth's orbit is nearly circular, minimizing seasonal extremes. Our axial tilt is moderate, neither too upright, which would eliminate seasons, nor too tilted, which would create extreme seasons. This orbital sweet spot has existed throughout recorded human history, providing the predictable conditions that allowed us to develop agriculture, build cities, and create complex societies. But this stability won't last forever. In about 10,000 years, the precession of Earth's axis will cause the northern hemisphere to experience winter when Earth is farthest from the Sun, intensifying seasonal contrasts. In about 25,000 years, Polaris will no longer be the pole star. Earth's axis will point toward Vega instead. In 100,000 years, Earth's orbit will be more elliptical, creating stronger variations in the intensity of seasons. These future changes will happen slowly enough for life to adapt, as it has throughout Earth's history. But they remind us that the current configuration of our orbit, which seems so permanent and stable, is actually just one phase in a continuing cycle of orbital evolution. Our descendants will experience a different Earth, with different seasonal patterns and climate zones, all because of subtle changes in how Earth falls around the Sun. The biological rhythms entrained by our orbital motion extend far beyond human physiology. Every organism on Earth has evolved in the context of reliable orbital cycles. Deciduous trees drop their leaves in response to shortening days. Birds migrate thousands of kilometers, triggered by changing day length and sun angle. Coral reefs spawn simultaneously on specific nights, coordinated by lunar and solar cycles. Flowers open and close at particular times of day, tracking the sun's apparent motion across the sky. These behaviors are so deeply encoded that they persist even when organisms are removed from natural light cycles. Trees brought indoors continue to attempt seasonal changes. Birds in constant laboratory conditions still show migratory restlessness at the appropriate times of year. This persistence reveals that orbital rhythms are not just environmental responses but are written into the genetic code of life itself. The evolution of photosynthesis, that fundamental process that powers most life on Earth, is perfectly tuned to our orbital distance from the Sun. Chlorophyll absorbs light most efficiently in the blue and red portions of the spectrum, which happen to be the wavelengths that penetrate Earth's atmosphere most effectively at our orbital distance. If Earth orbited closer to or farther from the Sun, if we received light of different intensity or spectrum, photosynthesis as we know it might not work. Even the chemistry of life shows orbital influences. The rate of chemical reactions depends on temperature, which depends on solar heating, which depends on our orbital distance and the angle of sunlight. Enzymes in our bodies are optimized to work at temperatures maintained by Earth's position in the habitable zone. The pH of the oceans, crucial for marine life, is buffered by chemical processes that depend on temperature cycles driven by our orbit. Our technological civilization has developed remarkable ways to measure and monitor these orbital influences. GPS satellites must account for Earth's rotation and orbital motion to provide accurate positioning. Their clocks must be adjusted for relativistic effects, time dilation due to their orbital velocity, and gravitational redshift due to their altitude. Without these corrections, GPS positions would drift by about 10 kilometers per day. Weather satellites in geostationary orbit, hovering above fixed points on Earth's equator, must be precisely positioned to maintain their station. They orbit at exactly the right altitude, 35,186 kilometers, where their orbital period matches Earth's rotation. But even these satellites feel the subtle influences of solar radiation pressure and the gravitational pull of the Moon and Sun, requiring occasional adjustments to maintain their positions. The International Space Station, orbiting much lower at about 400 kilometers, experiences significant atmospheric drag despite the extreme thinness of the atmosphere at that altitude. This drag causes the station's orbit to decay by about 2 kilometers per month. Regular rocket burns are needed to boost it back to its proper altitude, fighting against the tendency to fall toward Earth. The station is in a constant battle between falling too fast and not falling fast enough, maintaining the delicate balance needed for a stable orbit. Even our efforts to combat climate change are tied to orbital mechanics. Solar panels are most efficient when oriented perpendicular to incoming sunlight, requiring tracking systems that follow the sun's apparent motion across the sky, a motion created by Earth's rotation and orbit. Wind turbines harvest energy from atmospheric circulation, ultimately driven by differential solar heating. Proposals for space-based solar power would place collectors in orbit where they could receive constant sunlight, beaming energy back to Earth. The search for life elsewhere in the universe focuses heavily on orbital considerations. The concept of the habitable zone, that range of orbital distances where liquid water can exist, guides our search for Earth-like exoplanets. We look for worlds that fall around their stars at just the right distance, with just the right orbital characteristics to potentially support life. Every potentially habitable world we discover is another example of successful orbital balance, another place where the fall has been sustained long enough for complexity to potentially emerge. The recent discovery of exoplanets in the habitable zones of red dwarf stars raises interesting questions about how different orbital configurations might affect life. These planets orbit much closer to their dim stars, often tidally locked with one face in permanent daylight and the other in eternal darkness. Life on such worlds, if it exists, would experience orbital rhythms completely unlike our own. There would be no day-night cycle, no seasons as we know them. Yet these worlds are still falling around their stars, still maintaining that crucial balance between gravity and momentum. As we contemplate our cosmic future, orbital mechanics becomes even more critical. Proposals for terraforming Mars must account for its longer year, 687 Earth days, and its more elliptical orbit, which creates greater seasonal variation than Earth experiences. A Martian colony would need to adapt to a completely different set of orbital rhythms, days that are 24 hours and 37 minutes long, seasons that last nearly twice as long as Earth's, dust storms that can engulf the entire planet when Mars is closest to the Sun. Even more ambitious proposals imagine moving Earth itself, gradually shifting our orbit outward to compensate for the Sun's increasing brightness. This could theoretically be accomplished using repeated gravitational assist from asteroids, carefully orchestrated over millions of years. It would be the ultimate expression of orbital engineering, actively managing our fall around the Sun to maintain habitable conditions. We would become shepherds of our own orbit, no longer passive passengers, but active navigators of our cosmic journey. The possibility of interstellar travel raises questions about how humans might adapt to life without orbital rhythms. A generation ship travelling between stars would need to artificially recreate the cycles that our biology expects. Without the natural cues of sunrise and sunset, without seasons, without the subtle gravitational variations of orbital motion, humans might struggle physically and psychologically. We are so deeply tuned to our fall around the Sun that leaving it behind might be one of the greatest challenges of becoming an interstellar species. Yet even interstellar travellers would still be falling. They would fall through the galaxy, influenced by the gravitational pull of billions of stars. They would fall through the universe, participating in the cosmic expansion. The fall never ends, it just changes character, from closed orbits around single stars to open trajectories through vast spaces. We are falling creatures in a falling universe, and perhaps that's what makes us feel so at home in our perpetual tumble around the Sun. As you lie there in the darkness, feeling the solid earth beneath you, remember that this sensation of stillness is an illusion created by shared motion. You, your bed, your room, the air you breathe, all of it is falling together around the Sun at 30 kilometers per second. The glass of water on your nightstand doesn't spill, not because it's still, but because it's falling at exactly the same rate as everything around it. You're in perfect free fall, following the curved path that the Sun's gravity carves through space-time. This fall connects you to every human who has ever lived. Your ancestors navigated by the stars, planted by the seasons, celebrated the solstices and equinoxes. They didn't know they were falling around the Sun, but they felt its effects in the rhythm of days and years. They built monuments aligned with orbital events, Stonehenge marking the summer solstice, Mayan pyramids aligned with Venus's greatest elongation, Egyptian temples oriented toward the rising of specific stars. These ancient structures are testimonies to humanity's deep connection with cosmic motion. Modern life often disconnects us from these natural rhythms. Electric lights let us ignore the sunset. Climate control lets us ignore the seasons. Global commerce brings us summer fruits in winter. We can fly across time zones faster than our bodies can adapt. Yet our biology still expects the orbital rhythms that shaped our evolution. Jet lag, seasonal depression, sleep disorders. These are the prices we pay for defying the cosmic cycles that our bodies anticipate. But we can't truly escape our orbital reality. Every atom in your body is subject to the Sun's gravity. Every chemical reaction in your cells is influenced by the temperature maintained by our orbital distance. Every breath you take contains oxygen produced by photosynthesis, powered by sunlight at our specific orbital radius. You're not just on a planet orbiting the Sun, you're made of matter organized by billions of years of stable orbital conditions. You are, in a very real sense, a manifestation of Earth's successful fall around the Sun. The stability of this fall has given life the time it needed to explore countless forms and possibilities, from the first simple cells to the complex ecosystems we see today, from the first nervous systems to conscious minds capable of understanding their own cosmic motion. All of this was made possible by the reliable, consistent, billions of years-long fall of Earth around the Sun. We exist because our planet found a stable orbit and kept it, maintaining conditions suitable for life while so many other worlds failed. Think about what this means. Every thought you've ever had, every feeling you've ever experienced, every memory you hold dear, all of these exist because Earth maintains its orbit. If our planet were falling differently, if we were spiraling into the Sun or drifting into the cold darkness, consciousness as we know it could never have emerged. Our minds, capable of contemplating the universe, are products of successful orbital mechanics. We are the universe's way of understanding its own tendency to fall. As sleep approaches, as your consciousness begins its nightly fade, you're participating in another cycle tied to our cosmic motion. Sleep itself may have evolved in response to the day-night cycle created by Earth's rotation. It's more efficient to be inactive during the darkness than to maintain the metabolic cost of nighttime activity. Sleep is our biological acknowledgement of Earth's spin, our cellular surrender to the rhythm of light and shadow that has played across our planet's surface for billions of years. In your dreams tonight, you might fly, freed from the sensation of gravity. But even in sleep, you're still falling, still tracing your path around the Sun. Your sleeping body maintains its circadian rhythms, hormones rising and falling in patterns tied to Earth's rotation. Your brain consolidates memories in cycles that roughly match the orbital periods that have governed life since its beginning. Even unconscious, you remain a cosmic dancer, moving to the music of the spheres. Tomorrow, when sunlight wakes you, remember that those photons left the Sun's surface 8 minutes ago, travelled 150 million kilometers across space, and found you exactly where orbital mechanics predicted you would be. The reliability of that light, the certainty that the Sun will rise, the confidence that seasons will change and return, all of this emerges from the stability of our fall. We can make plans, build futures, dream of tomorrows because Earth's orbit is stable enough to guarantee that tomorrow will come. We are the inheritors of 4.5 billion years of successful orbital motion. Every generation of life that came before us managed to survive and reproduce within the conditions created by Earth's fall around the Sun. We carry their legacy in our genes, their adaptations to orbital rhythms encoded in our DNA. We are the current carriers of a torch that has been passed from organism to organism for billions of years, all of us children of the same stable orbit. And we are perhaps the first organisms capable of understanding and appreciating this inheritance. We can calculate our orbit, predict it millions of years into the future and past. We can compare it to the orbits of other worlds, understand what makes it special. We can even imagine changing it, engineering our cosmic trajectory to extend the habitability of our world. We have become conscious participants in our own orbital story. This consciousness brings responsibility. We are the first species capable of significantly affecting Earth's ability to support life, though not yet capable of affecting its orbit. The climate we're changing still depends on orbital cycles, but we're adding our own influences on top of those natural variations. We're conducting an uncontrolled experiment with the only known habitable world, the only successful long-term orbit that we know has produced conscious life. Yet understanding our cosmic motion also brings perspective. The challenges we face, while serious, are tiny compared to the stability of Earth's orbit. Climate change might disrupt civilization, but it won't stop Earth from falling around the Sun. Nuclear war might devastate the biosphere, but it won't alter our orbital trajectory. Even if humans disappear, Earth will continue its cosmic dance, and life in some form will likely continue to ride along, adapting to whatever conditions emerge. This perspective isn't meant to minimize our challenges, but to place them in context. We are cosmic beings dealing with cosmic-scale processes. The same intelligence that allowed us to understand our fall around the Sun can help us solve the problems we've created. The same curiosity that led us to discover orbital mechanics can guide us towards sustainable ways of living on our orbiting world. We are problem-solving apes on a falling rock, and recognizing our situation is the first step toward wisely managing it. As you drift towards sleep, let the knowledge of our cosmic motion bring you peace. You are held by forces that have been reliable for eons. The same physics that keeps galaxies spinning keeps you safe in your bed. The fall that seems dangerous is actually your protection, the motion that prevents catastrophe. You can rest knowing that Earth will continue its orbit tonight, tomorrow, for millions of tomorrows to come. You are part of something magnificent, something that transcends your individual existence while including it completely. You're a temporary arrangement of atoms that have been falling through space for billions of years and will continue falling long after you're gone. But for this moment, for these precious years of consciousness, you get to experience the fall, to understand it, to marvel at it. You get to be the universe aware of itself, falling through itself, contemplating its own motion. And now, as we approach the end of our journey through the mechanics and meaning of planetary motion, as we prepare to return to the question that started this exploration, remember that you're not just learning about Earth's fall around the Sun, you're participating in it. Every second that passes, you travel another 30 kilometers through space. Every heartbeat happens at a unique position in the cosmos. You're not separate from this story. You're its current chapter, written in flesh and consciousness, temporary but precious, finite but part of something infinite. The fall continues, reliable as physics, beautiful as mathematics, profound as existence itself. And you continue with it, safe in Earth's embrace, carried by forces you can trust, falling forever and never landing, missing the sun by just the right amount to create this moment of understanding, this night of rest, this peace that comes from knowing your place in the cosmic dance. We return now to where we began, to that seemingly simple question that contains universes of complexity. Why is every planet slowly falling into the sun, and why don't we notice? But now, after our long journey through the mechanics of orbits, the subtleties of forces, the measurements of spacecraft and the implications for life, we can see this question in a new light. We understand that the question itself contains a beautiful paradox. We are falling, and not falling simultaneously, plunging toward the sun while never getting closer, perpetually missing our star in the most elegant way possible. The answer, we've discovered, is not a single truth, but a symphony of truths playing together. Yes, every planet is falling toward the sun, accelerating toward it at every moment under the relentless pull of gravity. Earth accelerates toward the sun at about 6 millimeters per second squared, a tiny but constant tug that would, if we were stationary, pull us into our star in just 64 days. This fall is as real as the fall of an apple from a tree, governed by the same universal law of gravitation that shapes everything from raindrops to galaxies. But we're not stationary. We're moving sideways at tremendous speed, 30 kilometers per second for Earth, and this sideways motion transforms our fall from a straight plunge into an eternal circle. We fall toward the sun, but the sun's surface curves away from us in the geometry of space-time at exactly the rate we fall. We're like a satellite orbiting Earth, forever falling but never landing, except our satellite is a planet and our Earth is the sun. And yet, even this picture is too simple. We've learned that planets aren't falling into the sun at all. They're actually slowly drifting away as our star loses mass through fusion and solar wind. Earth recedes from the sun by about 1.5 centimeters per year, a glacially slow expansion that will continue as long as the sun shines. The solar system is gradually expanding like a slowly inflating balloon, maintaining its proportions while growing in scale. But even this isn't the complete picture. There are countless subtle forces at work: radiation pressure, tidal interactions, gravitational waves, the Yarkovsky effect, each contributing its tiny influence to planetary motion. These forces push and pull in different directions, some trying to make planets spiral inward, others pushing them outward, creating a complex balance that evolves over cosmic time. The real motion of planets is the sum of all these effects, a delicate equilibrium that has remained stable for billions of years. We don't notice this fall for the most profound reason of all. We're falling together. Everything around us, the ground beneath our feet, the air we breathe, the water in our oceans, is falling at exactly the same rate. There's no relative motion between us and our immediate environment that would let us sense the fall. We're like passengers in the smoothest vehicle ever created, Earth itself, travelling through space so perfectly that a glass of water sits undisturbed on a table while we hurtle through the cosmos at speeds that dwarf anything in human experience. Einstein deepened this understanding by showing us that falling is the natural state of motion in curved space-time. We're not being pulled by the sun so much as following the geometry of space that the sun's mass creates. We're like marbles rolling in a curved bowl, following the path of least resistance through the landscape of space-time. Our fall is not a deviation from natural motion, but the purest expression of it. This brings us to a beautiful realization. The reason we don't notice we're falling is that falling, in the cosmic sense, is the same as floating. When everything falls together, when there's no fixed reference frame to measure against, the distinction between falling and floating disappears. The astronauts in the International Space Station float because they're falling around Earth. We don't float because Earth's gravity gives us a different reference frame. But relative to the Sun, we're in exactly the same situation as those astronauts, in perpetual freefall. The stability of this fall is perhaps the most remarkable thing about it. Computer simulations show that Earth's orbit is stable for at least the next few billion years. Despite all the subtle forces, despite the gravitational tugs from other planets, despite the gradual changes in the Sun's mass, our orbit remains robust. We're not teetering on the edge of disaster, but settled into a deep groove in the fabric of space-time, a path that resists deviation. This stability has profound implications. It means that life had the time it needed to evolve from simple chemistry to conscious beings capable of understanding their own cosmic motion. It means that the rhythms and cycles that govern life on Earth, day and night, summer and winter, have been reliable enough for organisms to evolve deep dependencies on them. It means that we can make plans for the future, confident that Earth will continue its orbit for countless generations to come. But perhaps the deepest insight from our exploration is this. We are not separate from this cosmic motion, observing it from outside. We are manifestations of it, products of billions of years of stable orbital conditions. Every atom in our bodies has been falling through space for eons. Our biological rhythms are tuned to orbital cycles. Our consciousness itself emerged from the stability provided by Earth's perpetual fall around the Sun. When we look at the night sky and see other planets, we're seeing other worlds engaged in their own eternal falls. Mars, rusty and cold, falls around the Sun in 687 days. Jupiter, massive and majestic, takes nearly 12 years to complete its orbit. Saturn, with its beautiful rings, requires almost 30 years. Each one has found its own stable solution to the problem of falling, its own way of missing the Sun forever. And when we look beyond our solar system, we see that falling is universal. Every planet we've discovered around other stars is falling, maintaining its orbit through the same balance of gravity and momentum that keeps Earth safe. Every moon orbiting those planets is falling. Every star in every galaxy is falling around the galactic center. Every galaxy is falling through space, pulled by the gravity of other galaxies and dark matter. The entire universe is a vast network of objects falling around, toward and past each other in an intricate cosmic ballet. This universality of falling reveals something fundamental about the nature of existence. Motion is more natural than stillness. Curves are more common than straight lines. Balance emerges from opposing tendencies rather than from stasis. The universe is dynamic, not static, and we exist within that dynamism, not apart from it. The question, why don't we notice, has an even deeper answer than the physics we've explored. We don't notice because this is all we've ever known. Every human who has ever lived has lived on a falling world. Every experience we've ever had has been shaped by orbital motion. We have no reference point for what it would be like not to be falling around the Sun. It would be like a fish trying to notice water. It's so fundamental to our existence that it becomes invisible. But through science, through careful observation and mathematical reasoning, we've made the invisible visible. We've discovered our own motion, mapped our trajectory through space, understood the forces that shape our path. This is one of humanity's greatest intellectual achievements, the recognition that what feels like stillness is actually tremendous motion, that what seems like stability is actually a perfectly balanced fall. And in discovering our fall, we've discovered our connection to everything else. The same gravity that holds us to Earth holds Earth to the Sun to the galaxy, galaxies to clusters. We're part of a vast gravitational web that connects every piece of matter in the universe. When we understand our fall around the sun, we understand our place in this web, our participation in the fundamental processes that shape reality. The instruments we've built, the spacecraft exploring our solar system, the telescopes peering into deep space, the gravitational wave detectors sensing ripples in spacetime itself, are extending our awareness of this cosmic motion. Each measurement adds another decimal place to our understanding, another layer of subtlety to the picture. We're not just falling, we're learning to measure our fall with extraordinary precision, to predict it far into the future, to understand it in the context of the universe's evolution. And perhaps most remarkably, we're learning to use our understanding of orbital mechanics to explore beyond Earth. Every spacecraft we launch is an exercise in controlled falling. We've learned to use gravity as a tool, slingshotting spacecraft around planets to gain speed, aerobraking in atmospheres to slow down, entering orbits around other worlds. We've become masters of falling, turning what might seem like helplessness into a means of exploration. The future promises even greater mastery. We might learn to adjust Earth's orbit, moving our planet outward to compensate for the sun's increasing brightness. We might build vast structures in space that maintain their positions through careful orbital balance. We might send spacecraft to other stars, falling through interstellar space for thousands of years before falling into orbit around distant suns. Each achievement would be another chapter in our relationship with orbital motion, another way of working with, rather than against, the tendency of everything to fall. But for tonight, for this moment of quiet contemplation, the simple knowledge of our fall is enough. You don't need to do anything about it, don't need to worry about it, don't need to even think about it most of the time. Earth has been falling around the sun for 4.5 billion years without your conscious participation, and it will continue falling long after you're gone. You can trust in the physics, rest in the stability, sleep in the knowledge that you're held by forces that have been reliable since before life began. As you close your eyes, as your breathing deepens and your mind begins to drift toward dreams, you're still falling. The Earth beneath you is curving through space, following its ancient path around the sun. You're travelling at 30 kilometers per second, but because everything around you moves with you, it feels like perfect stillness. This is the paradox and the beauty of orbital motion. Tremendous, speed that feels like rest, eternal falling that never arrives, perpetual motion that requires no effort. In your dreams, you might experience the sensation of falling, that sudden drop that sometimes jolts us awake. But remember, you're always falling, whether awake or asleep, whether aware of it or not. The difference is that Earth's fall around the sun is stable, controlled, safe. It's not the terrifying plunge of nightmares, but the gentle spiral of cosmic dance, a fall that has continued for eons and will continue for eons more. Tomorrow the sun will rise, not because the sun moves, but because Earth's rotation carries you around to face our star again. The seasons will continue their progression, not because of changing distance from the sun, but because of Earth's tilted axis presenting different faces to solar radiation. The years will pass, each one a complete orbit, another circuit in our eternal fall. And through it all, you'll be carried along, a conscious passenger on a cosmic journey that began long before you and will continue long after. We've travelled far in our exploration tonight, from Newton's falling cannonball to Einstein's curved space-time, from the solar wind to gravitational waves, from the birth of the solar system to its far future. We've seen how Earth's orbit affects everything from the length of our days to the evolution of life, from our biological rhythms to our technological civilization. We've discovered that we're not just on a falling world, but are made of falling matter, organized by billions of years of stable orbital conditions into the remarkable patterns we call life. And through it all, we've found that the answer to our original question is both simple and profound. Every planet is slowly falling into the sun because gravity never stops pulling. We don't notice because we're falling too, along with everything around us, in such perfect synchrony that it feels like stillness. But planets are also slowly drifting away from the sun as it loses mass, adding another layer to the story. The real picture is one of exquisite balance, multiple forces in equilibrium, creating the stable orbits that make life possible. This is the true wonder of planetary motion. Not that planets fall, but that they fall so perfectly, so consistently for so long, It's a testament to the elegant mathematical laws that govern our universe, laws that create stability from motion, permanence from change, life from the endless dance of matter and energy through space and time. As our journey together draws to a close, as these words fade into the silence of night, remember that the story continues. Earth continues its fall around the sun. The sun continues its journey around the galaxy. The galaxy continues its motion through the universe. And you continue with all of it, a brief but precious consciousness aware of its own cosmic motion, capable of understanding its place in the grand dance of existence. You are stardust organized by gravity into a pattern capable of contemplating gravity. You are fallen matter that has learned to understand falling. You are a temporary arrangement of atoms that have been orbiting the sun for billions of years, and for this brief moment those atoms have come together in a configuration that can appreciate the journey. This is the gift of consciousness, not to stop the fall or change it, but to understand it, to find meaning in it, to recognize the beauty of our perpetual tumble through the cosmos. The night deepens around you. Your body relaxes into sleep, trusting the stability of Earth's surface even as that surface hurtles through space. Your breathing slows to a rhythm older than consciousness, a rhythm tuned to a world that has been falling around its star since before life began. And as you drift into dreams, you carry with you the knowledge that you're part of something vast and beautiful, the eternal fall of worlds around stars, the cosmic dance that creates the conditions for existence itself. Sleep now, carried by the same forces that carry the planets. Rest in the embrace of physics, held by the same gravity that holds galaxies together. Dream in the safety of Earth's orbit, knowing that you'll wake tomorrow still falling, still safe, still part of this magnificent cosmic journey. The fall continues, as it has for billions of years, as it will for billions more. And you continue with it, a conscious witness to the universe's most fundamental dance, the dance of matter falling through space-time, creating patterns of such beauty and complexity that they can look back and understand themselves. In the morning, when light returns, remember this night's journey through the cosmos. Remember that you're not stuck on a rock floating in space, but are actively participating in a dynamic process that connects you to everything else in the universe. Remember that the stability you feel is actually motion, that the stillness is actually speed, that the safety comes from falling in just the right way. And perhaps in that remembering you'll find what humans have always sought in their contemplation of the heavens, a sense of place, of purpose, of connection to something greater than ourselves. We are falling beings in a falling universe, and recognizing this doesn't diminish us but elevates us. We are the universe becoming aware of its own motion, consciousness emerging from cosmic dance, meaning arising from the mathematical poetry of orbital mechanics. The story we've shared tonight is both ending and continuing. These words are concluding, but Earth's orbit goes on. Our exploration is complete, but the reality it describes persists. You've learned about your cosmic motion, but you've been participating in it all along. Nothing has changed except your awareness, and yet that changes everything. You now know you're falling, understand why you don't feel it, appreciate the forces that keep you safe. This knowledge is a gift from the generations of humans who looked up at the sky and wondered, who tracked the planets and calculated their paths, who built instruments to measure what couldn't be seen, who pieced together the story of our cosmic dance from countless observations and calculations. You are the heir to this knowledge, the current carrier of humanity's understanding of its own motion through space. Carry it gently, this knowledge of our fall. Let it bring you wonder rather than fear, connection rather than isolation, peace rather than anxiety. You're exactly where physics says you should be, moving exactly as the laws of nature dictate, safe in the embrace of forces that have been reliable since the beginning of time. There is nowhere to fall to because you're already falling. There is nothing to hold on to because everything is falling with you. There is nothing to fear because the fall is stable, sustainable, beautiful in its mathematical precision. And now, as our cosmic contemplation comes to its close, as the last words approach and silence prepares to return, take with you this final thought. You are not a passenger on Spaceship Earth, watching the cosmos from inside. You are part of the cosmos, made of cosmic matter, shaped by cosmic forces, participating in cosmic motion. Your fall around the sun is not something happening to you, but something you're doing actively, continuously, perfectly. The universe doesn't carry you. You help compose it. Gravity doesn't trap you. You express it. The orbit doesn't confine you. You embody it. You're not subject to cosmic forces, but are a manifestation of them, a temporary but genuine expression of the universe's tendency to organize matter into patterns of increasing beauty and complexity. Tomorrow you'll wake and go about your day, perhaps forgetting that you're falling through space at tremendous speed. But your body won't forget. It will maintain its circadian rhythms, respond to the angle of sunlight, prepare for the coming season. Your atoms won't forget. They'll continue their billions of years old journey through space, temporally organized as you but eternally in motion. And somewhere deep in your consciousness, below the level of daily thoughts and concerns, you'll carry the knowledge that you're part of something magnificent, something that transcends your individual existence while including it completely. This is the final gift of understanding our fall around the sun, the recognition that we belong here, that we're not accidents or anomalies but natural expressions of cosmic processes. We exist because the universe tends toward complexity, because gravity creates stable orbits, because stars shine steadily for billions of years, because planets can fall forever without landing. We are proof that the universe is not just vast and violent, but also capable of creating islands of stability where consciousness can emerge and contemplate its own existence. The night is deep now, perfect for sleep, perfect for letting go of conscious thought and trusting the deeper rhythms that govern our existence. You've journeyed far tonight, from the mechanics of orbits to the meaning of existence, from the measurements of spacecraft to the mysteries of consciousness. You've discovered that you're falling and that it's safe, that you're in motion, and that it feels like stillness, that you're part of something vast and that you belong completely. Let these thoughts settle into your bones, into the calcium forged in dying stars, into the marrow that creates your blood, into the cells that maintain your life. Let the knowledge of your cosmic motion become part of you, not as an abstract concept, but as a felt truth, a bodily understanding that you're held, that you're safe, that you're exactly where you need to be. The story ends here, but the fall continues. The words cease, but the orbit persists. Our shared contemplation concludes, but your journey through space goes on, second by second, breath by breath, heartbeat by heartbeat. You are a falling being who has learned about falling, a cosmic dancer who has glimpsed the choreography, a temporary pattern of matter that has understood its own impermanence and found peace in it. Sleep comes now, carried on the same wave that carries Earth around the sun. Dreams approach, as inevitable as tomorrow's sunrise, as gentle as gravity's pull. Your consciousness fades, but your atoms continue their ancient journey, falling through space as they have for billions of years, as they will for billions more. And in this ending that is not an ending, in this conclusion that concludes nothing but our words, in this final moment of our shared contemplation of cosmic motion, we return to silence. Not the silence of emptiness, but the silence of completion, of understanding achieved, of questions answered and mysteries preserved. The silence of space itself, through which Earth falls without sound, carrying us all toward tomorrow, toward the future, toward whatever comes next in our eternal, beautiful, perfectly balanced fall around our star. Good night, fellow traveller. Sleep well in your fall through space. Dream sweetly in Earth's embrace. Rest peacefully knowing that you're held by forces that have never failed, carried by motions that will continue long after all human words have faded into silence. You are safe in your cosmic fall, perfect in your orbital motion, exactly where you belong in the vast, turning, falling universe. The fall continues, the dance goes on, and you are part of it all, forever and perfectly, falling through the cosmos with grace.